Welcome to the first 150-year history of humans post-colonization of Venus. Part 1, Above the Inferno. The journey to colonize Venus began not with a dramatic proclamation or a single heroic mission, but with decades of methodical scientific advancement and careful planning. While Mars had long captured the public imagination as humanity's second home, a dedicated group of researchers, engineers, and visionaries had been quietly making the case for Venus, a world that, at first glance, seemed utterly inhospitable to human life. Venus, our closest planetary neighbor, presents a study in extremes. Its surface is a vision of hell itself, hot enough to melt lead at 462 degrees Celsius, with crushing atmospheric pressure 90 times that of Earth at sea level, and clouds of sulfuric acid that rain corrosive droplets that never reach the ground before re-evaporating in the intense heat. For decades, even robotic probes struggled to survive more than hours on this unforgiving surface. But 50 kilometers above that inferno lies a different Venus entirely, one that, in many ways, is more Earth-like than any other place in our solar system. Here, in the upper atmosphere, pressure and temperature fall to near-Earth conditions. It was this band of habitability that the Venus Cloud Colony initiative targeted for humanity's most ambitious off-world settlement. In year one of the Venus colonization timeline, after 6 months of interplanetary travel, the cloudship Morning Star arrived in Venusian orbit, carrying the first expedition team and the components for Cloud Haven 1, humanity's first permanent outpost in the atmosphere of another world. The cloudship itself was a marvel of engineering, combining a traditional spacecraft with a high-altitude deployment vehicle designed specifically for Venus's unique conditions. The team's first challenge came immediately: the deployment of the initial atmospheric entry vehicle. Unlike Mars missions with their 7 minutes of terror, during descent, Venus presented a different kind of challenge, a controlled descent that would stop at precisely the right altitude, neither continuing down to the crushing pressure below nor rising too high into the thin upper atmosphere. The deployment vehicle, nicknamed Gossamer, detached from the orbiting cloudship and began its careful descent. As it encountered the upper fringes of Venus's atmosphere, it began to slow, its heat shield glowing from atmospheric friction. Unlike Earth or Mars landers, Gossamer was never designed to reach the surface. Instead, at a carefully calculated altitude, it deployed its most revolutionary feature, an enormous reinforced envelope that began to fill with a mixture of nitrogen and oxygen brought from Earth. This was the key insight that made Venus colonization possible. In the carbon dioxide-rich atmosphere of Venus, standard breathable air, 21% oxygen, 79% nitrogen, acts as a lifting gas, much like helium does on Earth. The habitation module, suspended beneath this enormous air-filled balloon, slowed and then achieved neutral buoyancy precisely at the 52-kilometer altitude mark, exactly where conditions were most Earth-like. The first transmissions from the floating outpost arrived on Earth approximately 5 minutes later. Cloud Haven 1 deployed and stable. We're floating in the clouds of Venus. The initial weeks aboard Cloud Haven 1 focused on systems verification and atmospheric analysis. The exterior sensors confirmed what decades of probe data had suggested. Outside the habitat, the temperature hovered around a very manageable 25 degrees Celsius, with atmospheric pressure only slightly lower than Earth sea level. Through the viewports, the early colonists observed a perpetual golden haze, sunlight filtering through the upper cloud layers, with occasional glimpses of the dense, reflective cloud deck below. Cloud Haven 1 represented the culmination of decades of research into making such a habitat possible. Its hull incorporated three critical technological breakthroughs. The primary envelope used multi-layered carbon fiber materials reinforced with nanotubes for strength while maintaining low weight. The second breakthrough was in the realm of self-healing polymers that could automatically seal small punctures, critical in an environment where a habitat failure would be catastrophic. But perhaps most important was the third innovation, an outer coating made of advanced fluoropolymers specifically engineered to resist the corrosive effects of sulfuric acid. Early Venus probe failures had demonstrated that conventional materials quickly degraded in Venus's clouds. The development of these acid-resistant coatings, now commonly known as Venuskin, represented one of the most significant materials science advancements of the pre-colonization era. Early Venuskin relied on a refined version of polytetrafluoroethylene, similar to the material used in non-stick cookware, but with added compounds that actively neutralized acid on contact. Later versions incorporated nanomaterials that created an almost impenetrable barrier against corrosion, while still remaining lightweight and flexible enough for habitat construction. Life aboard Cloud Haven 1 quickly settled into routines dictated by the unique environment. The habitat followed Venus's powerful wind currents, circling the planet approximately every 4 Earth days. This created a novel day-night cycle for the inhabitants, roughly 2 Earth days of sunlight followed by 2 Earth days of darkness as the habitat drifted around the night side of Venus. The colonists adapted their schedules to this extended cycle, developing a unique work pattern with longer activity periods followed by longer rest periods. Sleep researchers on Earth monitored these adaptations closely, noting that after initial adjustment difficulties, many colonists reported improved sleep quality with the longer day-night cycle, leading to adjustments in lighting systems to create an artificial extended Venus day aboard the habitat. By year 2, Cloud Haven 1 had proven the viability of the floating colony concept, and preparations began for expanding the outpost. The first major addition was the atmospheric processing module, a critical component for long-term sustainability. While the initial habitat was stocked with supplies from Earth, true colonization would require utilizing Venus's own resources. The processing module began the crucial work of in situ resource utilization. Its primary function was carbon dioxide electrolysis, splitting the abundant carbon dioxide in Venus's atmosphere into oxygen for breathing and carbon that could be used in manufacturing. Early versions of these processors operated at about 40% efficiency, requiring significant power from the habitat's solar arrays, which captured the abundant sunlight, almost twice as intense as on Earth due to Venus's closer proximity to the Sun. A secondary but equally revolutionary process involved the extraction of water from an unlikely source, the very sulfuric acid clouds that made Venus seem so hostile. Through a carefully controlled chemical reduction process using catalysts, hydrogen sulfide was split from sulfuric acid and then further processed to yield water molecules. Though energy-intensive, this process proved that the elements for water existed in Venus's clouds, validating a critical aspect of the colony's long-term viability plan. By year 3, these atmospheric harvesting operations were providing nearly 30% of the colony's oxygen needs and a small but crucial supply of water, supplementing the reserves brought from Earth. This proof of concept was celebrated as a major milestone, the first example of humans living off the land on another world. Life in Cloud Haven 1 was challenging in ways both expected and surprising. The habitat itself, while engineering a stable internal gravity environment thanks to Venus's near-Earth gravity, about 90% as strong, still experienced occasional turbulence as it rode the atmospheric currents. Colonists described the sensation as similar to being on a large ship at sea, mostly stable with periodic gentle swaying during stronger winds. Sensitive instruments and equipment required specialized mounting to account for this constant subtle motion. Communication with Earth faced unique challenges as well. When Cloud Haven 1 drifted around to Venus's far side, direct Earth communication became impossible. This led to the deployment of a constellation of communication relay satellites in Venusian orbit, ensuring continuous contact regardless of the habitat's position in its atmospheric journey around the planet. Perhaps the most unexpected challenge came from the psychological impact of the environment itself. Looking out from Cloud Haven 1, colonists saw neither the star-filled blackness of space that Moon and Mars settlers experienced, nor the familiar blue skies and landscapes of Earth. Instead, they were surrounded by an endless golden haze, above, below, and in all directions. Some colonists reported a distinct form of disorientation they called cloud blindness, a temporary loss of spatial awareness due to the lack of visual reference points. Habitat designers addressed this by creating false horizon lighting systems around viewport edges and developing regular drone flights that provided visual reference points outside the habitat. By year 4, most colonists had adapted to this unique visual environment, and some even reported finding beauty in the ever-changing patterns of Venus's clouds. In year 4, as Cloud Haven 1 continued to prove the viability of atmospheric habitation, the colony experienced its first major crisis. A confluence of atmospheric conditions created what came to be known as the acid storm crisis, a period of unusually high concentration of sulfuric acid in the cloud layers surrounding the habitat. Monitoring instruments detected the increasing acidity, but the rate of increase surpassed all models and predictions. Within hours, the exterior Venuskin coating was experiencing degradation rates 10 times higher than designed parameters. Damage assessment drones revealed that certain sections of the habitat's upper envelope were thinning dangerously, with the acid eating through the protective layers faster than the self-healing properties could respond. The colony initiated emergency protocols, adjusting altitude to seek less acidic cloud layers while deploying the recently developed atmospheric maintenance units, specialized drones equipped with sprayers that applied additional protective polymer coatings to the weakened sections of the habitat exterior. For 72 tense hours, repair operations continued around the clock, while the habitat systems were placed on minimal operations to reduce any stress on the structure. Engineers later determined that a rare combination of atmospheric circulation patterns had concentrated sulfuric acid droplets to levels not previously recorded by probes or satellites. The crisis ultimately passed without habitat breaches, but it prompted an accelerated research program into improved coding technologies and early warning systems for detecting dangerous acid concentrations. More importantly, it provided valuable data on worst-case scenarios that informed all future habitat designs. By year 5, Cloud Haven 1 had not only survived but thrived. Its population had grown with the arrival of additional specialists, and plans were already underway for a second, larger habitat. The initial atmospheric outpost had definitively proven the floating colony concept, and demonstrated solutions to the major challenges of living in Venus's clouds. One of the most significant developments in Year 5 was the first, locally sourced construction materials, carbon fibers created from processed atmospheric carbon dioxide. While still experimental and limited in application, this achievement represented a crucial step towards self-sufficiency. As the 5th year of Venus colonization concluded, the inhabitants of Cloud Haven 1 celebrated a remarkable milestone. They had established and maintained human presence in one of the most challenging environments ever attempted. Their floating outpost, constantly circling the planet on Venus's powerful winds, had transformed a world once thought utterly hostile to life into humanity's second off-world home. The challenges had been immense, the solutions innovative, and the lessons learned invaluable. Cloud Haven 1 had demonstrated that with the right technology and approach, even a world as seemingly inhospitable as Venus could be colonized. The cloud ships were no longer merely theoretical. They were now home to the most isolated human settlement in history, floating serenely above an inferno in the golden clouds of Earth's sister planet. Part 2: Building the Sky Bridge. The success of Cloud Haven 1 marked just the beginning of humanity's ambitious journey to establish a permanent presence in the clouds of Venus. As the colony entered its 5th year, attention turned toward expansion, sustainability, and creating the infrastructure necessary to support a growing presence in Venus's atmosphere. The pioneering floating habitat had proven the concept viable, but a true colony would require much more than a single outpost. Year 6 began with the establishment of the Venus Orbital Transfer Station, a crucial piece of infrastructure that would revolutionize supply logistics between Earth and the Venusian colony. Prior to this, all supplies had to be delivered directly from Earth-launched vessels to Cloud Haven 1, a complex rendezvous procedure requiring precise timing and perfect execution as the habitat drifted through Venus's atmosphere. The transfer station, positioned in a stable Venusian orbit, created a permanent waypoint where supply ships from Earth could dock regardless of Cloud Haven 1's position in its atmospheric circuit around the planet. From this orbital platform, smaller atmospheric shuttles, designed specifically for the transition from space to Venus's upper atmosphere, would ferry supplies down to the floating habitat on a regular schedule. This two-stage delivery system dramatically improved efficiency and safety. Supply missions from Earth could now be optimized for the interplanetary journey without needing to carry the specialized equipment required for atmospheric entry. Meanwhile, the shuttles operating between orbit and Cloud Haven 1 could be specifically engineered for repeated transitions between vacuum and Venus's dense atmosphere. The transfer station grew steadily over the next several years as additional modules were delivered from Earth. By Year 8, it had evolved into a small space station with permanent crew quarters, extensive storage facilities, and maintenance bays for the atmospheric shuttles. This orbital outpost became known informally as Sky Bridge, reflecting its role as the crucial link between Earth and the Venusian clouds. Sky Bridge also served another vital function. It provided a safe haven in case emergency evacuation of the cloud colony ever became necessary. The knowledge that an escape route existed brought considerable psychological comfort to the colonists below, who were acutely aware of their vulnerable position floating above Venus's hellish surface. While Sky Bridge was taking shape in orbit, plans for a second atmospheric habitat were already well underway. Cloud Haven 2, designed with lessons learned from the first habitat, would be significantly larger and incorporate numerous technological improvements. Its construction began in year 7 with the delivery of the primary envelope components to Venus orbit. The deployment of Cloud Haven 2 presented new challenges compared to the original habitat. Rather than simply establishing another isolated outpost, the plan called for Cloud Haven 2 to operate in relative proximity to Cloud Haven 1, with the eventual goal of linking the habitats together. This required precise control over each habitat's position within Venus's atmosphere, a considerable challenge given the powerful and sometimes unpredictable wind currents. The solution came in the form of advanced propulsion systems integrated into the new habitat's design. Unlike Cloud Haven 1, which largely drifted with the atmospheric currents, Cloud Haven 2 featured multiple electric fan arrays powered by high-efficiency solar panels. These fans couldn't counteract Venus's strongest winds, but they provided enough thrust to make gradual position adjustments, allowing the habitat to maintain a relatively stable position relative to Cloud Haven 1. Cloud Haven 2 successfully deployed in Venus's atmosphere during year 8. With nearly twice the interior volume of the original habitat, it was designed primarily as a research and manufacturing center, complementing Cloud Haven 1's role as the primary living quarters and administrative hub. The new habitat featured expanded atmospheric processing capabilities, dedicated laboratory spaces, and the colony's first true manufacturing facility. Perhaps the most ambitious element of Cloud Haven 2 was the experimental farm module, a dedicated section designed to grow food crops using hydroponic systems. While Cloud Haven 1 had contained small garden areas for fresh vegetables, the farm module represented the first large-scale attempt at food production in Venus's atmosphere. The abundant sunlight available at Venus, almost twice as intense as on Earth, provided excellent growing conditions once filtered to appropriate levels, and the controlled environment allowed for optimized growing conditions. By year 9, the farm module was producing leafy greens, tomatoes, and several fast-growing vegetable varieties, providing a welcome supplement to the colony's packaged food supplies from Earth. Though still far from self-sufficiency, this agricultural success represented another crucial step toward a sustainable colony. The presence of two habitats necessitated a solution for travel between them. Initially, this was accomplished using small transporter pods, essentially miniature versions of the habitats themselves, using the same breathable air buoyancy principle, but sized for just a few passengers. These pods could make the journey between habitats in approximately 6 hours, a lengthy commute that limited exchange between the outposts. By year 10, the colony had implemented a more permanent connection, the aerial causeway. This revolutionary structure consisted of a lightweight but extremely strong carbon fiber tether system connecting the two habitats, with an enclosed transport tube that allowed pressurized travel between them. The causeway had to be flexible enough to absorb the constant subtle movements of both habitats while maintaining structural integrity, a remarkable engineering achievement that drew on principles from suspension bridge design. With the causeway in place, travel time between habitats reduced to under an hour, effectively creating a single distributed colony rather than two separate outposts. This marked the beginning of what would eventually become a network of interconnected habitats floating through Venus's clouds. While the colony expanded in the relatively hospitable cloud layers, scientific interest in Venus's surface remained strong. In year 7, the colony deployed its first surface exploration robot, the Venus Ground Explorer, or VGE-1. Unlike previous short-lived surface probes, VGE-1 incorporated revolutionary high-temperature electronics developed specifically for Venus's extreme conditions. Traditional silicon-based electronics fail almost immediately at Venus surface temperatures of 462 degrees Celsius. VGE-1 instead utilized silicon carbide circuits designed to function in these extreme conditions, along with specialized mechanical systems that required no conventional lubricants, which would evaporate instantly in the heat. Deployment of VGE-1 required a specialized descent vehicle that protected the explorer during its passage through Venus's atmosphere before releasing it for landing. The descent took approximately 1 hour, with the explorer touching down on a relatively flat plain in Venus's northern hemisphere. VGE-1 transmitted the first high-definition images from Venus's surface, revealing a barren, rock-strewn landscape bathed in an eerie orange light filtered through the dense atmosphere. The rover carried a suite of instruments, including a drill capable of extracting small core samples from Venus's rocks, providing the first direct analysis of surface minerals since the brief Soviet Venera missions decades earlier. The data from VGE-1 revolutionized our understanding of Venus's geological history. Analysis of the surface samples revealed evidence that Venus may have had Earth-like conditions billions of years ago, including potential oceans, before a runaway greenhouse effect transformed it into the scorching world we see today. This discovery heightened interest in Venus not just as a colony site, but as a crucial case study in planetary climate evolution. Despite its robust design, VGE-1 operated for only 42 days before succumbing to the harsh conditions, still a remarkable achievement compared to previous surface missions measured in hours. Its success led to plans for more advanced surface explorers and established the concept of a surface-to-cloud scientific pipeline, where materials gathered from the surface could potentially be transported up to the habitats for more detailed study. The growing complexity of operations both in orbit and throughout Venus's atmosphere brought new risks, highlighted tragically in year 11 with the loss of Skywing 5. The Skywing Atmospheric Survey Craft series had been developed to explore Venus's complex atmospheric dynamics, gathering data critical for both scientific understanding and colony safety. These unmanned aerial vehicles used a combination of buoyancy and electric propellers to navigate through different atmospheric layers. Skywing 5 was conducting routine monitoring of lower cloud formations when it encountered what would later be classified as a superstorm, a powerful atmospheric disturbance generated by the interaction of Venus's super-rotating atmosphere with thermal upwellings from the hot surface below. The storm's intensity exceeded anything previously recorded, with vertical wind shears reaching speeds of over 320 kilometers per hour. Contact with Skywing 5 was lost approximately 6 minutes after it reported entering the disturbance. Recovery efforts located debris several days later, spread across thousands of kilometers as the storm had completely disintegrated the craft. Analysis of the final data transmissions provided valuable information about these previously theoretical superstorms, but came at the cost of losing an important research platform. The Skywing 5 disaster prompted a complete overhaul of atmospheric operations safety protocols. New storm prediction models were developed based on the data recovered, and strict operational boundaries were established for different classes of aerial vehicles. Most significantly, a network of automated weather monitoring stations was deployed throughout Venus's atmosphere, creating an early warning system for detecting dangerous weather patterns before they fully developed. This tragedy also accelerated the development of more robust atmospheric vehicles. The next generation of Skywing craft featured reinforced frames, multiple redundant communication systems, and the ability to rapidly ascend to safer atmospheric layers when dangerous conditions were detected. The Skywing 5 Memorial Laboratory, established in Cloud Haven 2, continued the important atmospheric research that the lost craft had begun, ensuring that its scientific mission would continue. By year 12, the colony's focus had shifted significantly toward resource self-sufficiency. While the orbital transfer station ensured regular supply deliveries, the long-term viability of the colony depended on reducing reliance on Earth. This led to the development of the Atmospheric Mining Initiative, a program designed to harvest useful materials directly from Venus's clouds. The primary targets for atmospheric mining were carbon, from carbon dioxide, sulfur, and oxygen, from sulfuric acid and nitrogen, present at about 3.5% in Venus's atmosphere. These elements form the building blocks for many essential materials, from breathing gases to construction components. The initiative deployed specialized drone fleets designed to operate at different atmospheric layers. High-altitude drones collected nitrogen from the upper atmosphere, while mid-level drones focused on carbon dioxide processing. Lower-level collectors, operating in the most acidic cloud layers, gathered sulfuric acid for water production and sulfur extraction. These drones operated on a continuous cycle, gathering materials and returning to processing platforms attached to the habitats. By year 13, atmospheric mining operations were providing nearly 70% of the colony's oxygen needs and a steadily increasing supply of water through acid conversion processes. The excess carbon was used to produce carbon fiber for construction and manufacturing, reducing the need to import structural materials from Earth. The most significant innovation in atmospheric mining came with the development of the acid conversion array in year 14. This dedicated processing platform, tethered below Cloud Haven 2, specifically targeted the water from acid challenge that had been a limiting factor in colony growth. The array utilized a catalytic conversion process that broke down sulfuric acid into water, oxygen, and sulfur compounds with unprecedented efficiency. The process still required significant energy input, provided by dedicated solar arrays, but it increased water production rates by over 300% compared to previous methods. For the first time, the colony could produce enough water not just for basic survival needs, but for expanded agriculture and limited manufacturing processes that required water input. Throughout these years of infrastructure development and resource harvesting advancements, the Venusian colony maintained its scientific mission. The unique environment provided research opportunities that were impossible elsewhere, leading to breakthroughs that benefited not just the colony but humanity as a whole. Perhaps the most significant research contributions came in materials science. The harsh, acidic environment of Venus's clouds had driven the development of corrosion-resistant materials far beyond what had been available before colonization. These advances spread to Earth applications, revolutionizing industries from chemical manufacturing to maritime engineering. The colony's laboratories developed an entire family of advanced fluoropolymers and composite materials with unprecedented resistance to chemical degradation. These materials, collectively marketed on Earth under the brand name Venuskin in honor of their origins, found applications in everything from industrial storage tanks to medical implants. Some economists estimated that the licensing of Venus-developed materials technologies alone had offset nearly 30% of the colony's establishment costs by year 15. Another research breakthrough came in atmospheric carbon capture technology. The methods developed to extract and process carbon dioxide from Venus's atmosphere proved adaptable to Earth's climate mitigation efforts. More efficient carbon capture systems, based on Venus colony technology, began deployment on Earth to address rising carbon dioxide levels, creating an unexpected environmental benefit from the colonization program. Life support recycling technologies saw tremendous advancement as well. The closed-loop systems developed for the Venus habitats achieved water and air recycling rates approaching 99% efficiency, far beyond previous space habitat capabilities. These technologies transferred to Earth applications in water-scarce regions and other off-world habitats, improving resource efficiency throughout human civilization. By the 15-year mark, the Venus colony had transformed from an experimental outpost to a permanent, growing presence in the clouds of our sister planet. With two primary habitats connected by the aerial causeway, a supporting orbital infrastructure, and increasing self-sufficiency through atmospheric resource harvesting, the foundation had been laid for long-term human habitation. The colony faced ongoing challenges. The harsh environment remained ever-present, resource limitations required constant innovation, and the isolation from Earth took psychological tolls despite regular communication and supply deliveries. Yet these 15 years had proven beyond doubt that humans could not only survive, but thrive in one of the most unlikely habitats in the solar system. As Cloud Haven 1 and 2 drifted through the golden clouds of Venus, linked by their sky bridge and supported by their growing fleet of specialized vehicles and drones, they represented one of humanity's greatest achievements, turning a world once considered completely inhospitable into a place where humans could live, work, and even begin to prosper. The Sky Bridge era had established the critical infrastructure that would support the next phase of Venusian colonization, the development of a true society among the clouds. Part 3: Society in the Clouds. With the physical infrastructure of Cloud Haven 1 and 2 firmly established, and the Sky Bridge connecting them creating a unified colony, the focus during years 15 through 25 shifted toward developing the social structures necessary for a thriving civilization. The floating habitats were no longer merely places to survive. They were becoming a home, a community, and the birthplace of a new branch of human society uniquely adapted to life in the clouds of Venus. As the population of the Venusian colony grew beyond the original scientific teams to include specialists in various fields, maintenance workers, agricultural experts, and eventually families, the need for formal governance became apparent. The initial mission command structure, with its clear hierarchy and Earth-based oversight, was insufficient for a permanent settlement with increasingly diverse needs and perspectives. In year 16, representatives from all colony sections gathered for what came to be known as the First Cloud Convention. This week-long series of meetings, held in the newly completed assembly chamber of Cloud Haven 2, laid the groundwork for the colony's governance structure. After considerable debate, the convention established the Venusian Atmospheric Administrative Council, a governing body designed specifically for the unique challenges of managing a society suspended in the clouds of another world. The Venusian Atmospheric Administrative Council consisted of 7 elected council members representing different aspects of colony life: habitat systems, scientific research, resource management, agriculture and food production, education and culture, external relations, and general welfare. This diversity ensured that all critical areas of colony function had representation in decision-making processes. A unique aspect of the Venusian Atmospheric Administrative Council was its balanced approach to autonomy and Earth connection. While the colony remained technically under the authority of the International Venus Colony Initiative that had funded and organized the mission, the physical distance and communication delays made immediate oversight impractical. The Venusian Atmospheric Administrative Council was therefore granted significant self-governance authority for day-to-day operations, while maintaining coordination with Earth for major decisions and resource allocations. This model was formalized in the Venus Colonial Charter, ratified in year 17, which outlined not only the powers and limitations of the Venusian Atmospheric Administrative Council, but also the rights and responsibilities of all colony inhabitants. The charter notably included the right to return, guaranteeing any colonist the option to return to Earth when supply missions allowed, and the resource equity principle, which established that Venus's atmospheric and eventually surface resources belonged to the colony as a whole rather than any individual or subgroup. The legal framework established by the Charter was neither fully Earth-based nor entirely novel. It adapted existing space law, particularly the Outer Space Treaty's principles regarding the use of celestial bodies, while creating new concepts specifically for the Venusian context. The Charter explicitly prohibited any individual or group from claiming exclusive territory in Venus's atmosphere or surface, establishing instead a stewardship model where the colony managed resources for the benefit of humanity's presence on Venus. This governance structure reflected the practical realities of Venusian life. With limited space and resources, cooperation was not merely desirable but essential for survival. The interdependence of all colonists created a natural tendency toward collective decision-making and resource sharing that became codified in the colony's formal structures. While governance developed, a more organic process was also underway, the emergence of a distinctly Venusian culture. By year 18, the first children born on Venus, nicknamed Cloud Citizens, were beginning to shape colony life in unexpected ways. These children, never having experienced Earth directly, perceived the floating habitats not as alien environments, but simply as home. The adaptation to Venus's unique rhythm became particularly apparent in these first-generation Venusians. Rather than struggling to adapt to the colony's 4-day cycle of day and night as the habitats circled the planet, they found it entirely natural. Linguists noted that Cloud Citizens developed specific terminology for different phases of this cycle. Terms like high bright for when the habitat was on the Venus sun side with maximum illumination, soft light for the diffused twilight periods, and deep dark for the middle of the night side transit. Education in the colony adapted to both the practical needs of survival in this unusual environment and the preservation of Earth's cultural heritage. The curriculum developed for Cloud Citizens included standard subjects, but with a distinctly Venusian perspective. Geography classes, for instance, studied both Earth's continents and Venus's surface features that the children would never directly experience, but above which they constantly floated. Technical education received particular emphasis, with even young children learning the basics of habitat systems and safety protocols. By necessity, every Venusian needed to understand at least the fundamentals of how their floating world functioned and what to do in various emergency scenarios. This created a highly technically literate population where even art and culture were infused with an awareness of the engineered environment that sustained them. Cultural traditions unique to Venus began to emerge during these years. The crossing ceremony, marked a habitat's transition from Venusian day to night as it drifted around the terminator line. During this event, colony lights would be gradually adjusted to create a ceremonial transition, often accompanied by music and shared meals. What began as a practical notification of the day-night shift evolved into an important cultural moment that brought the community together. The Founders' Remembrance became an annual colony-wide event commemorating the initial deployment of Cloud Haven 1. During this day, historical accounts of the early mission were shared, especially with children, and the names of all who contributed to the colony's establishment were honored. This tradition helped maintain a connection to the colony's origins and reinforced the values of courage and innovation that had made Venusian settlement possible. Even artistic expression took on distinctly Venusian characteristics. Cloud sculpting, creating three-dimensional art using lightweight, suspended materials that moved gently with the habitat's subtle motions, became a popular form unique to Venus. Music compositions often incorporated the ambient sounds of the habitat systems or the occasional external sounds of acid droplets on the protective outer layers, creating what became known as atmosphere harmonics. The gastronomy of Venus developed distinctive traits as well, adapting to the limited but increasingly diverse agricultural output of the colony's expanding farm modules. Vertical garden spaces throughout both habitats supplemented the main agricultural areas, allowing colonists to grow herbs and small vegetables in their living quarters. Cloud cuisine became known for its efficient use of available ingredients, vibrant presentation to counter the monotony of the golden external environment, and the incorporation of carefully cultivated spices that provided psychological comfort through varied flavors. As this unique society developed, a fundamental question emerged that would shape the colony's future direction. Should Venus remain primarily a scientific outpost with limited population, or should it actively expand to accommodate larger numbers of settlers from Earth? This question, which came to be known simply as the Great Debate, dominated colony discourse during years 20 through 22. The scientific continuity faction argued that Venus's primary value was as a research platform. They pointed to the groundbreaking work already accomplished in atmospheric science, materials development, and extreme environment adaptation. This group cautioned that rapid population growth would strain resources, potentially compromise research objectives, and might lead to deteriorating safety standards as accommodation pressure increased. In contrast, the expansion advocates maintained that a larger, more diverse population was essential for long-term viability. They argued that the colony needed a broader skills base, greater genetic diversity, and the economic activity that additional inhabitants would generate. This group emphasized the symbolic importance of Venus as a second home for humanity, not merely a research station. The debate played out in formal council sessions, community forums, and countless personal conversations throughout the colony. It also engaged participants from Earth, where potential future colonists and supporting agencies had their own perspectives on Venus's optimal development path. The resolution, reached in year 22, was a compromise embodied in the Balanced Growth Accord. This agreement established a carefully managed expansion plan that would increase the colony's population at a sustainable rate while preserving its scientific mission. The accord called for construction of a third major habitat specifically designed for additional residential capacity, alongside expanded resource harvesting operations to support the growing population. Crucially, the accord established the principle of capability-based growth, The colony would expand only as its life support systems, resource production, and safety margins allowed, rather than according to a predetermined schedule. This pragmatic approach acknowledged the harsh realities of Venusian life, while setting the stage for gradual but steady growth. The implementation of this expansion plan required significant enhancements to the colony's logistical networks. The aerial causeway connecting the first two habitats had demonstrated the concept's viability, but a true network capable of supporting multiple habitats and facilitating efficient movement of people and materials required more sophisticated solutions. In year 23, the colony deployed the first of a new class of inter-habitat transport vehicles, the atmospheric transit shuttles. These specialized airships, using the same buoyancy principles as the habitats themselves, but incorporating powerful electric propulsion systems, could travel between habitats much faster than movement along the fixed causeways. The shuttles established regular routes connecting all colony facilities, creating a public transportation system suspended in Venus's clouds. These shuttles were complemented by cargo-specific variants designed to move larger volumes of supplies, harvested resources, and manufacturing materials between habitats. The development of standardized docking interfaces on all habitats and auxiliary structures facilitated smooth transfers and minimized the time spent during potentially hazardous external operations. The transportation network expanded to include smaller personal transport pods for emergency use or specialized travel needs. These single or dual-occupant vehicles provided flexibility for researchers needing to visit atmospheric sampling stations or maintenance teams addressing issues at remote facilities. By year 24, this evolving transportation system supported not just movement between the main habitats, but also connections to the growing constellation of specialized facilities distributed throughout the colony's operational region. Atmospheric processing platforms, solar energy collection arrays, research outposts at various altitudes, and the construction site for Cloud Haven 3. The effectiveness of this network depended on reliable communication, which led to one of the colony's most significant infrastructure projects during this period, the Venusian Atmospheric Relay Network. Prior to this development, communication between habitats and with Earth relied on a combination of direct radio links when geometry allowed, and the orbital relay satellites that had been deployed during the colony's early years. This system, while functional, suffered from occasional interruptions and capacity limitations that became increasingly problematic as the colony grew. The Relay Network project addressed these issues through a comprehensive communication infrastructure designed specifically for Venus's unique environment. The core of the network consisted of 12 advanced communication platforms deployed at strategic locations in Venus's upper atmosphere. These platforms, essentially specialized miniature habitats containing powerful transmission and reception equipment, maintained constant positioning using the same propulsion technology developed for position control of the main habitats. These communication hubs created a mesh network, providing total coverage of the colony's operational region regardless of the habitat's positions in their atmospheric circuits around Venus. The network used encrypted optical data transmission for high-bandwidth habitat-to-habitat communication, with redundant radio systems as backup. For communication with Earth and the orbital facilities, powerful dedicated uplinks maintained constant connection. The relay network revolutionized colony communications in ways that extended beyond basic connectivity. With sufficient bandwidth now available, colonists gained access to entertainment and educational content from Earth that had previously been limited. Real-time video conferencing with family on Earth became possible when orbital alignments were favorable, reducing the psychological isolation that many colonists experienced. Perhaps most importantly, the network enabled the implementation of the colony-wide integration system, a comprehensive data platform that monitored all critical habitat systems, resource levels, personnel locations, and environmental conditions. This system provided both automated management of routine operations and early warning of potential issues, significantly enhancing colony safety. The value of this integrated monitoring system was demonstrated dramatically in year 25 during what became known as the pressure cascade incident. The event began with what appeared to be a minor pressure fluctuation in a seldom-used storage section of Cloud Haven 1. The integrated monitoring system detected not just this initial anomaly, but also subtle changes in adjacent sections that suggested a potential spreading problem. Based on this early detection, the system triggered a compartment isolation protocol, sealing affected sections before human operators would have recognized the emerging pattern. Investigation teams discovered that a section of the habitat's internal pressure hull had developed microscopic stress fractures that were beginning to propagate along a seam. Had the problem remained undetected, it could have developed into a catastrophic decompression event affecting multiple habitat sections. The incident, while ultimately contained without injuries, highlighted a critical vulnerability in the original habitat design. Cloud Haven 1, as the first habitat, had been constructed with a single primary pressure hull supplemented by compartmentalization. Analysis of the stress fracture pattern revealed that the habitat's continuous flexing as it moved through Venus's atmospheric currents had, over years, created material fatigue in certain key structural elements. In response, the colony initiated the most extensive retrofitting project in its history. Over the next 18 months, Cloud Haven 1 received a complete internal reinforcement system that created a hull within a hull design, essentially adding a complete secondary pressure vessel inside the original structure. This approach, already incorporated into Cloud Haven 2's design and enhanced further for the under-construction Cloud Haven 3, became the standard for all Venusian habitats. The pressure cascade incident and the subsequent redesign work led to the codification of what became known as the Venus Habitat Safety Principles, a comprehensive set of design and operational guidelines that emphasized redundancy, continuous monitoring, and proactive maintenance. These principles stated that all critical systems must have at least triple redundancy, that no single failure point should be capable of compromising habitat integrity, and that aging infrastructure must be replaced based on predetermined service life rather than waiting for signs of failure. These stringent requirements added to the cost and complexity of Venusian habitats, but established a safety record that would prove remarkable given the hostile environment. In the decades that followed, this approach to habitat design would be credited with preventing numerous potential disasters and would eventually influence habitat engineering throughout the solar system. As the colony reached the 25-year mark, it had transformed from an experimental outpost into a functioning society with its own governance, culture, infrastructure, and outlook. The population had grown to nearly 500 permanent residents, with plans for continued expansion as Cloud Haven 3 neared completion. Resource self-sufficiency had increased dramatically, with over 80% of oxygen and water needs met through local production. The Venusian colony had developed a distinct identity, neither fully separate from Earth nor merely an extension of terrestrial society. The cloud citizens, particularly those born on Venus who now ranged from young children to early adolescence, embodied this new identity most fully. They moved through the floating habitats with an intuitive comfort that Earth-born colonists never quite achieved, navigating both the physical environment and the social structures that had evolved to support life in this most unlikely of homes. The foundation had been laid for what would become one of humanity's most remarkable achievements, a thriving civilization suspended in the clouds of a world that, just 25 years earlier, had been considered too hostile for human habitation. The next phase of Venusian colonization would build on this foundation, extending humanity's reach not just through the clouds, but eventually toward the forbidding surface below. Part 4, the Mining Challenge. By the 25th year of Venus colonization, the floating habitats had achieved remarkable success in harvesting atmospheric resources. Carbon, oxygen, and nitrogen extracted from Venus's clouds supplied many of the colony's basic needs. The acid-to-water conversion systems provided a growing portion of the water supply, and the expanding agricultural modules were increasing food self-sufficiency. Yet as the colony continued to grow, a fundamental limitation became increasingly apparent. The atmosphere alone could not provide all the materials needed for a truly self-sustaining civilization. Metals, silicon, rare minerals, and various industrial elements remained entirely dependent on Earth supply missions. While the orbital transfer station ensured regular deliveries, the reliance on imported materials severely constrained manufacturing capabilities and long-term growth potential. Every kilogram launched from Earth came at tremendous expense, limiting what could be brought to Venus. As Cloud Haven 3 neared completion and population growth accelerated, colony planners recognized that accessing Venus's surface resources was not merely desirable but essential for the colony's future. The surface of Venus held abundant materials that would be invaluable to the floating habitats: iron, aluminum, titanium, silicon, and various other metals and minerals locked in Venus's rocky crust. Early surface analysis from the VGE-1 rover and subsequent probes had confirmed these resources existed in accessible concentrations. The challenge was not finding resources, but developing technology capable of operating in Venus's extreme surface conditions long enough to extract and transport them. Year 26 saw the official launch of Project Hephaestus, named after the ancient Greek god of blacksmiths and craft, a massive technological development program aimed at creating autonomous mining systems capable of functioning on Venus's surface. The project represented the colony's most ambitious engineering challenge to date, requiring solutions to problems that had never before been addressed. The surface conditions that Project Hephaestus needed to overcome were staggering. Temperatures of 462 degrees Celsius, hot enough to melt lead, combined with atmospheric pressure equivalent to being 900 meters underwater on Earth. Add to this the corrosive carbon dioxide atmosphere and the occasional sulfuric acid precipitation that never reached the ground before re-evaporating, and the result was an environment seemingly designed to destroy any human-made machine. Previous short-duration surface probes had relied primarily on passive cooling systems and specialized high-temperature components to function for brief periods. But mining operations would require extended functionality, mobility, power generation, excavation capabilities, and processing systems, a far more complex engineering challenge than simple data collection. The first breakthrough came with the development of what engineers called thermally isolated operational cores. Rather than attempting to cool entire machines, this approach isolated only the most temperature-sensitive electronics in heavily insulated chambers. These chambers used multi-layer vacuum insulation combined with phase-change cooling materials that absorbed heat through controlled melting, protecting critical components while allowing mechanical systems to operate at ambient temperature. For components that couldn't be thermally isolated, the project developed new silicon carbide and gallium nitride electronics designed to function at Venus surface temperatures. These high-temperature circuits couldn't match the complexity or speed of conventional electronics, but provided sufficient processing power for basic autonomous operations when combined with the isolated core systems. Power generation presented another significant challenge. Solar panels would be ineffective on the surface due to the thick cloud cover filtering most sunlight. Nuclear power, while reliable, raised concerns about deploying radioactive systems on another world. The solution came in the form of advanced thermoelectric generators that exploited the very heat that made Venus so hostile. These generators used the temperature difference between the superheated surface and slightly cooler internal components to directly generate electricity, essentially turning Venus's heat into a power source. While not particularly efficient by Earth standards, these generators provided a continuous, reliable energy supply without moving parts that could fail in the harsh conditions. For mobility and excavation, the project developed mechanical systems using specialized metal alloys and ceramic components capable of withstanding Venus's temperatures. Conventional hydraulics were replaced with mechanical linkages or compressed gas systems, and all lubricants were replaced with dry graphite or ceramic bearings. The resulting machines looked quite different from Earth mining equipment, bulkier, with fewer exposed moving parts and distinctive radiator arrays to manage waste heat from their operation. By year 30, Project Hephaestus had progressed from concept to functional prototypes tested in Venus simulation chambers on Earth. These chambers couldn't perfectly replicate Venus conditions for extended periods, but they provided sufficient validation to proceed with actual surface deployment. The first surface mining test platform, designated the Hephaestus Surface Extractor, or HSE-1, was prepared for deployment to Venus. The deployment of HSE-1 in year 31 represented a crucial test of the project's technologies. The bulky mining platform was delivered to Venus orbit aboard a dedicated cargo vessel and then transferred to a specialized descent craft. The craft's heat shield protected the platform during the fiery descent through Venus's upper atmosphere, with parachutes slowing its descent through the dense lower atmosphere before the final landing system engaged. HSE-1 touched down in a relatively flat region of Venus's southern hemisphere that orbital scans had identified as rich in accessible metal deposits. The first images transmitted from the platform showed a desolate, rock-strewn landscape bathed in the dim orange light that penetrates Venus's cloud layers. More importantly, all systems reported operational status despite the crushing pressure and extreme heat. Over the next 3 months, HSE-1 conducted the first true resource extraction operations on Venus. Its mechanical excavator arm broke through the rocky surface to expose the mineral-rich layers beneath, while onboard sensors analyzed the composition to identify the most valuable materials. A simple processing unit separated some elements directly on-site, creating concentrated materials that would be easier to transport than raw regolith. The test mission exceeded expectations, operating for 97 days before a mechanical failure in its main excavator arm ended the experiment. But the platform had proven the core concept. Autonomous mining on Venus was possible with the right technology. Analysis of the data and the small material samples returned via Ascent capsule provided invaluable insights for refining the next generation of surface mining systems. While the basic technology had been demonstrated, significant challenges remained in scaling up operations, and most crucially, in transporting harvested materials from the surface to the floating habitats 50 kilometers above. This led to a strategic reassessment known as the Highland Gambit. Venus's surface is not uniformly flat. It features mountain ranges, highlands, and massive shield volcanoes that rise several kilometers above the mean surface level. The Highland Gambit proposed focusing initial large-scale mining operations on these elevated regions, particularly Maxwell Montes, Venus's highest mountain range, where the peak rises approximately 11 kilometers above the surrounding plains. At these higher elevations, atmospheric pressure is reduced by approximately 20% compared to the lowest plains, and temperatures are 30 to 40 degrees Celsius cooler. While still extremely hostile by Earth standards, these slightly less severe conditions offered meaningful advantages for machinery longevity and operational capability. Additionally, the shorter distance to the floating habitats from these elevated points would simplify the resource transportation challenge. The Maxwell Montes region also offered promising geological features. Orbital mapping and surface analysis from previous probes indicated the mountain range contained significant deposits of metal-rich minerals, including iron and titanium compounds that would be particularly valuable for habitat construction and expansion. By year 33, the Highland Gambit strategy was formally adopted, and preparations began for what would become known as the Maxwell Montes expedition, the most ambitious surface mission yet attempted. While previous surface deployments had focused on single platforms operating independently, the expedition would establish a network of cooperating machines, forming the first permanent mining outpost on Venus's surface. The logistics of the expedition were staggering. Over a 6-month period, a series of specialized descent vehicles delivered components including drilling platforms, excavators, processing units, and a central control hub to a carefully selected plateau in the Maxwell Montes range. Each unit deployed with its own power generation system and communication equipment, but was designed to physically connect with the others to form an integrated facility. The cornerstone of the expedition was the Surface Ascent Vehicle, a revolutionary craft designed to solve the critical challenge of transporting materials from surface to habitat. Unlike rockets, which would require impossible quantities of fuel to launch conventionally from Venus, the Surface Ascent Vehicle utilized a 2-stage approach. The first stage employed a specialized lifting gas system. At surface level, the vessel would fill enormous high-temperature resistant balloons with carbon dioxide heated well above ambient temperature. Despite Venus's already hot conditions, this additional heating created enough buoyancy to lift the craft several kilometers upward. As the vessel rose and external pressure decreased, the heated gas expanded naturally, providing additional lift. Once the craft reached approximately 20 kilometers altitude, the second stage engaged, a series of electric propellers powered by fuel cells. These propellers would drive the craft upward through the less dense upper atmosphere until it reached the habitats at 50 kilometers. The entire system was designed to operate autonomously, requiring no human presence on the hazardous surface below. The Maxwell Montes mining outpost became operational in year 35, with all components successfully deployed and integrated. The facility established a routine of continuous operation. Excavators would gather raw materials that were then processed to separate valuable elements from waste rock. The concentrated materials would be loaded aboard the surface ascent vehicles for transport to the habitats above. Initial operations focused on titanium-rich ore deposits, as titanium's strength-to-weight ratio and corrosion resistance made it particularly valuable for habitat construction. The first successful surface-to-cloud material transfer occurred in year 36, delivering approximately 400 kilograms of processed titanium compounds to Cloud Haven 3. While modest in quantity, this delivery represented a transformative moment for the colony, the first utilization of Venus's surface resources for habitat construction. As the Maxwell Montes facility refined its operations, attention turned to scaling up the material transport system. The surface ascent vehicles, while functional, were complex and limited in capacity. This led to the development of what would become one of the colony's most iconic innovations, the supply tether concept. The supply tether proposed creating a direct physical connection between the surface mining facility and the habitats above using an ultra-strong, heat-resistant cable. Early designs called for a carbon nanotube composite core wrapped in protective ceramic layers, creating a structure capable of withstanding both the tremendous tension of spanning 50 kilometers vertically and the temperature gradient from surface to habitat level. Materials transport capsules would travel along this tether, using electric motors to climb upward, a far more energy-efficient approach than the balloons and propellers of the surface ascent vehicles. Additionally, the tether could carry power and communication lines, greatly simplifying operations at the mining facility. Initial reactions to the supply tether concept were skeptical. Many engineers considered the technical challenges insurmountable, particularly the need to maintain tension in a structure spanning such a distance through an atmosphere with complex wind patterns. Others questioned whether any material could withstand the temperature range and chemical environment from surface to cloud level over extended periods. Despite these concerns, theoretical models suggested the concept was feasible with sufficiently advanced materials. By year 38, a scaled prototype was under development. Rather than immediately attempting a full surface-to-cloud tether, the prototype would span a more modest 5 kilometers, connecting the mining facility to an intermediate collection platform that would then use conventional surface ascent vehicles for the remaining journey to the habitats. While surface mining development continued, the colony also faced the challenge of processing the incoming raw materials. Traditional refining methods used on Earth were often unsuitable for the floating habitats due to weight constraints, energy requirements, or process chemicals that would be hazardous in the closed environment. This necessitated the development of new approaches specifically adapted for Venus's unique circumstances. The solution came in the form of dedicated processing platforms, essentially specialized miniature habitats dedicated to refining and manufacturing. The first of these, the Vulcan processing platform, was deployed adjacent to Cloud Haven 3 in year 37. This facility used a combination of traditional metallurgical techniques and novel processes developed specifically for the Venusian context. One such innovation was the use of focused solar energy for high-temperature processing. Venus receives approximately twice the solar energy of Earth, and carefully designed reflector arrays could concentrate this energy to create the extreme temperatures needed for certain refining operations without consuming the colony's power supply. These solar furnaces became a distinctive feature of the processing platforms, with massive reflector arrays that tracked the sun during the daylight portion of the colony's atmospheric circuit around Venus. For chemical processing, the platforms pioneered closed-loop systems that captured and reused virtually all process materials, preventing both waste and potential habitat contamination. These systems were not always as efficient as their Earth counterparts, but they dramatically reduced the need for importing processed chemicals from Earth. By year 39, the Vulcan platform was successfully processing the increasing flow of materials from the Maxwell-Montes facility, producing refined metals and other materials for habitat construction and manufacturing. A second processing platform, Helios, began construction with a focus on semiconductor materials, silicon, and related elements needed for electronics and solar panel production. The growing success of surface mining operations led to an ambitious expansion of the Maxwell-Montes expedition in year 40. Additional excavation units were deployed to access deeper and more diverse mineral deposits, while automated survey drones began mapping other promising regions for potential mining sites. The prototype supply tether, after extensive testing and refinement, was extended to its full 5-kilometer length, establishing the proof of concept for the eventual full-length surface-to-cloud tether. The 40-year mark of Venus colonization thus saw a colony transformed by access to surface resources. Although atmospheric harvesting remained essential for life support materials, the addition of metals and minerals from the surface dramatically expanded manufacturing capabilities. Components that previously had to be imported from Earth at great expense could now be produced locally, accelerating habitat expansion and reducing dependency on supply missions. This period also saw the emergence of the first true Venusian industrial sector. A growing portion of the colony's population worked in resource processing, manufacturing, and the increasingly complex logistics of managing material flows between surface mines, processing platforms, and habitats. These industrial specialists developed unique expertise adapted to Venus's environment, skills that had no direct equivalent on Earth. Perhaps most significantly, the success of the Maxwell-Montes expedition changed how colonists perceived their relationship with Venus itself. The world beneath the clouds was no longer merely a hostile environment to be avoided, but a resource to be utilized. Venusian children learned about the topography of the surface they would never directly see, but upon which their future livelihood increasingly depended. As the colony prepared to enter its 5th decade, this evolving relationship with Venus's surface laid the groundwork for even more ambitious undertakings. The technologies developed for mining would eventually enable other surface activities, from expanded scientific research to potential direct human presence on the surface within specialized vehicles. The mining challenge had been met with characteristic Venusian ingenuity, turning one of the most hostile environments in the solar system into a vital resource for humanity's most improbable colony. The legacy of Project Hephaestus extended far beyond Venus itself. The high-temperature electronics, specialized materials, and autonomous systems developed for Venus surface operations found applications throughout human space activities and in extreme environments on Earth. Mining operations in Earth's deepest mines, underwater resource extraction, and even disaster response in hazardous conditions all benefited from technologies first pioneered to extract resources from from the inferno of Venus's surface. Part 5, the growth period. With the establishment of surface mining operations and the successful transport of materials from Venus's hostile surface to the floating habitats, the colony entered a transformative era of growth and development. Years 40 through 55 marked a period when the Venusian settlement evolved from a collection of research outposts into a genuine civilization among the clouds, with expanding infrastructure, growing self-sufficiency, and an increasingly distinct cultural identity. Agriculture had been part of the colony since its early days, with small hydroponic systems producing supplemental fresh food in Cloud Haven 1 and the larger farm module in Cloud Haven 2. However, these early agricultural efforts had been limited in scale and variety, providing only a fraction of the colonists' nutritional needs. As the population grew and greater self-sufficiency became imperative, a fundamental reimagining of food production became necessary. In year 41, the colony established the Venusian Agricultural Research Center in a dedicated section of Cloud Haven 3. This facility brought together botanists, environmental engineers, nutritionists, and autonomous systems specialists with a clear mandate: develop food production systems capable of supporting the entire colony using minimal resources and space. The research center's first breakthrough came with the development of optimized lighting systems for plant growth. Venus receives approximately twice the solar energy of Earth, but this light is filtered and scattered by the cloud layers, creating diffuse golden illumination rather than direct sunlight. Rather than trying to replicate Earth's sunlight precisely, the researchers designed specialized LED arrays that produced exactly the wavelengths most efficient for photosynthesis, while minimizing energy consumption. These lighting systems operated in tandem with reflector arrays that captured and concentrated external light during the daylight portion of Venus's 4-day cycle. During the nightside passage, when no external light was available, the agricultural sections switched entirely to LED lighting powered by the colony's energy storage systems. This approach created consistent growing conditions regardless of the habitat's position in its atmospheric circuit around Venus. The second innovation involved growing mediums and nutrient delivery. Traditional hydroponics used considerable water volumes, which remained a precious resource despite improvements in acid-to-water conversion efficiency. The research center developed what came to be called vapor phase aeroponics, a system where plant roots were suspended in air-filled chambers and nutrients were delivered via fine mist rather than liquid submersion. This approach reduced water usage by nearly 80% compared to conventional hydroponics, while accelerating plant growth due to increased oxygen availability to the roots. The system was further refined with recapture systems that collected and recycled nearly 99% of water vapor, creating a virtually closed-loop water cycle within the agricultural modules. Perhaps the most significant agricultural innovation was the development of vertically integrated growing systems that maximized food production per cubic meter of habitat space. Unlike Earth agriculture, which primarily utilizes horizontal surface area, Venusian agriculture developed in a three-dimensional manner, with plants growing not just on stacked horizontal trays, but also on vertical surfaces, and in specially designed rotational systems that moved plants through optimized environmental zones as they matured. These vertical farms became a characteristic feature of all Venusian habitats, with some agricultural sections extending through multiple habitat levels. The interiors of these spaces created lush, green environments that provided not just nutrition, but psychological benefits for colonists otherwise surrounded by technology, and the golden haze visible through external viewports. By year 45, these agricultural innovations had increased food self-sufficiency to over 60% of the colony's needs. The staple crops included fast-growing grains specially bred for the controlled environment, various leafy greens, vertical growing vegetables like tomatoes and peppers, and protein-rich legumes. Supplemental protein came from cultivated fungal sources, essentially highly efficient mushroom varieties, and specialized single-cell protein cultures, sometimes referred to as cloud protein, derived from genetically modified bacteria that could utilize carbon dioxide directly as a food source. The success of the agricultural systems had effects beyond mere nutrition. As fresh, locally grown food became more abundant, a distinctive Venusian cuisine began to emerge. Characterized by creative combinations of the available ingredients and influenced by the diverse cultural backgrounds of the colonists, cloud cuisine became known for its emphasis on fresh, vibrant flavors and artistic presentation to counteract the visual monotony of the external environment. Agricultural advancement was just one component of the broader expansion underway during this period. With increased access to building materials from the surface mining operations, the colony could manufacture structural components locally rather than relying on Earth supply missions. This manufacturing capability enabled more rapid habitat construction and expansion than had previously been possible. Cloud Haven 4, which began construction in year 42, represented the first habitat built primarily from Venus-sourced materials. Its primary structural components utilized titanium alloys processed from ores mined in the Maxwell-Montes region, while its internal systems incorporated locally manufactured components whenever possible. Only the most complex electronics and specialized equipment still required import from Earth. The habitat's design incorporated all the lessons learned from previous construction, including the hull-within-hull safety approach developed after the pressure cascade incident. It also featured more spacious living quarters and dedicated recreational areas, acknowledgement that as the colony transitioned from a scientific outpost to a permanent settlement, quality of life considerations became increasingly important. Cloud Haven 4 reached completion in year 46, adding capacity for an additional 200 colonists and extensive new manufacturing facilities. These facilities included the colony's first comprehensive electronics fabrication center, capable of producing control systems, sensors, and communication equipment that previously had to be imported from Earth. With 4 major habitats now operational and connected by the expanded transportation network, the colony leadership established an ambitious goal in year 47, the resource independence target. This initiative aimed to reduce dependency on Earth supplies to less than 50% within 5 years, covering all categories of resources from food and manufacturing materials to complex technology and medical supplies. The target was deliberately challenging, requiring innovations across multiple domains simultaneously. Task forces were established for each major resource category, with clear metrics for success and colony-wide coordination. This program generated a wave of innovation and efficiency improvements throughout the colony's operations. In the medical sector, for instance, the limited availability of pharmaceuticals from Earth led to an intensive investigation of synthesizing essential medications using locally available chemical precursors. The colony developed production capabilities for basic antibiotics, pain management medications, and preventive treatments, significantly reducing reliance on the Earth medical supply chain. Manufacturing saw similar advancements. The development of Venus-adapted 3D printing technologies allowed for the production of complex components using locally sourced materials. These systems utilized metal powders produced from surface-mined ores, as well as carbon-based materials derived from atmospheric carbon dioxide. By year 50, approximately 70% of replacement parts for habitat systems could be manufactured locally rather than imported. One of the most significant innovations emerged in the energy sector. While the colony had always utilized solar power, taking advantage of Venus's closer proximity to the Sun, earlier systems had been relatively small-scale and primarily attached directly to habitat structures. The resource independence target spurred the development of dedicated solar collection platforms, essentially specialized habitats whose primary purpose was capturing and distributing energy. The first of these, Solar Platform Alpha, was deployed in year 49. Unlike the habitats, which needed to balance multiple functions including living space, agriculture, and manufacturing, Solar Platform Alpha was optimized solely for energy production. Its upper surfaces were covered entirely with high-efficiency photovoltaic arrays designed to capture maximum solar energy during the daylight portion of Venus's day-night cycle. The platform incorporated massive energy storage systems using advanced flywheel technology rather than chemical batteries. These flywheels, spinning in vacuum-sealed chambers, stored kinetic energy when solar input was available and released it during the night-side passage, providing continuous power regardless of the platform's position relative to the Sun. Solar Platform Alpha dramatically increased the colony's available energy, enabling power-intensive operations that had previously been constrained. Within 2 years, 2 additional solar platforms were deployed, creating an energy infrastructure that not only met current needs, but provided capacity for continued expansion. By year 52, the resource independence target had been largely achieved, with Earth dependency reduced to approximately 45% across all categories. This achievement was celebrated throughout the colony with the first Independence Festival, a week-long series of events highlighting Venusian innovation and self-sufficiency. The festival became an annual tradition, reinforcing the colony's growing confidence in its ability to thrive in Venus's clouds through its own ingenuity. This growing self-sufficiency enabled the most ambitious habitat project yet, Cloud Haven 5, which began construction in year 53. Unlike previous habitats, which had balanced multiple functions including research, manufacturing, and residential space, Cloud Haven 5 was designed primarily as a residential habitat focused on providing comfortable, appealing living environments for the growing population. The habitat's design reflected a fundamental shift in thinking about long-term life on Venus. Earlier habitats had been engineered with efficiency and functionality as primary considerations, spaces where people could live safely while conducting scientific research or essential operations. Cloud Haven 5, in contrast, was designed with human comfort and psychological well-being as guiding principles. The habitat featured significantly larger personal living spaces, extensive communal areas including parks and recreation centers, and a central atrium with a carefully engineered water feature, a luxury made possible by improved water production from the acid conversion systems. Lighting throughout the habitat was designed to mimic Earth's daily cycle rather than Venus's 4-day pattern, creating a more familiar rhythm for residents while still accommodating the actual day-night cycle for external operations. Perhaps most striking were the enhanced viewing galleries, specially designed spaces with panoramic viewports where residents could observe the surrounding cloud environment. These galleries used advanced optics to enhance visibility and sometimes employed augmented reality systems to overlay information about visible cloud formations or distant habitats, creating a connection to the external environment that had been limited in earlier habitats. Cloud Haven 5 represented not just a functional expansion, but a statement about the permanence of human presence on Venus. Its design acknowledged that the floating colonies were not merely places where people would work temporarily before returning to Earth, but homes where generations might live entire lives. Construction progressed rapidly thanks to locally sourced materials and manufacturing capabilities, with completion targeted for year 56. As the physical infrastructure of the colony expanded, social and political evolution continued as well. The growing population, now numbering over 1,000 individuals, included not just original mission specialists and their replacements from Earth, but a significant number of Venus-born citizens with no direct experience of the home planet. This demographic shift, combined with increasing self-sufficiency, led to what historians would later call the social contract crisis. The crisis emerged gradually, beginning with debates in the Venusian Atmospheric Administrative Council about the colony's relationship with Earth authorities. Under the original mission framework, the Venus Colony Initiative, the international consortium that had funded and organized the colonization effort, maintained ultimate authority over major decisions, particularly those involving resource allocation and strategic direction. As the colony achieved greater self-sufficiency and developed local expertise adapted specifically to the Venusian environment, this arrangement became increasingly contentious. The catalyst for open debate came in year 54, when the Colony Initiative announced plans for a significant expansion of scientific facilities that would require deferring construction of additional residential space. This directive contradicted local planning that had prioritized housing to accommodate the growing population, particularly as Venus-born citizens reached adulthood and established their own households. The Administrative Council formally objected to the directive, marking the first significant public break with Earth authority. The debate quickly expanded beyond this specific issue to encompass fundamental questions about governance and sovereignty. Who should make decisions about Venus's development? The Earth-based organizations that provided ongoing financial support and specialized technology, or the colonists themselves who lived with the consequences of these decisions and had developed unique expertise in the Venusian context. Various factions emerged within the colony, ranging from those advocating complete autonomy from Earth to those preferring a more gradual evolution of the relationship. Public forums throughout the habitats hosted intense discussions about the colony's future direction and identity. These debates were particularly passionate among younger colonists, especially those born on Venus who felt less connection to Earth institutions. The Autonomy Alliance, a political movement that gained significant support during this period, argued that the colony had fulfilled its part of the original social contract by proving the viability of Venusian settlement and developing valuable technologies that benefited Earth. They maintained that the time had come for a new arrangement recognizing the colony's maturity and right to self-determination. In response, the Cooperative Framework Association emphasized the ongoing benefits of Earth connection, including access to technology, specialized expertise, and the wider human genetic pool that would be essential for the colony's long-term viability. They advocated for a reformed relationship rather than separation, with greater local autonomy while maintaining formal ties to Earth. These political divisions affected not just formal governance, but daily life throughout the habitats. Some colonists displayed free Venus symbols on their personal quarters or workstations, while others organized discussion groups focusing on maintaining Earth cultural heritage. Family units sometimes found themselves divided along generational lines, with Venus-born children questioning their parents' continued allegiance to Earth institutions. The tensions came to a head in year 55, when a scheduled delivery of specialized manufacturing equipment was delayed in favor of sending additional scientific instruments requested by Earth-based researchers, but not prioritized by the colony. This relatively minor logistical decision became symbolic of the larger governance issue, leading to a coordinated work slowdown in non-essential services throughout the colony, the first organized political action of its kind on Venus. The Administrative Council, caught between pressure from residents and their formal obligations to the colony initiative, convened an emergency constitutional convention with representatives from all habitats and major professional sectors. This convention, lasting 3 intensive weeks, drafted what became known as the Venus Accord, a proposed new framework for colony governance and Earth relations. The Accord acknowledged the continuing importance of Earth support while establishing greater local autonomy in key areas, particularly internal resource allocation, habitat design, and expansion planning. It created a more formalized democratic structure for colony governance and explicitly recognized certain rights for Venus-born citizens. Most significantly, it established a timeline for transition to full self-governance within 15 years, with clearly defined milestones and mutual obligations. The document was transmitted to Earth with a formal request for negotiation based on its principles. As year 55 came to a close, the colony awaited Earth's response, knowing that the relationship between humanity's home world and its most remote settlement stood at a pivotal moment. The social contract crisis had brought to the surface tensions that had been building for years, forcing both the colony and Earth authorities to reconsider fundamental assumptions about how humans would govern themselves beyond Earth. Despite these political tensions, the growth period had transformed the Venusian colony from an experimental outpost to a viable civilization with its own infrastructure, culture, and identity. The floating habitats, now numbering 5 with more under construction, supported a growing population with increasingly Earth-independent capabilities. Agricultural innovations provided a varied diet of locally grown food, manufacturing facilities produced most essential equipment, and the energy infrastructure captured the abundant solar resources of Venus's orbit. Most importantly, the colonists had developed a deep understanding of their unique environment, creating technologies and practices specifically adapted to life in Venus's clouds. This expertise, born of necessity and ingenuity, would prove invaluable in the decades to come, as the colony faced new challenges and opportunities in its continuing evolution as humanity's most improbable settlement. Part 6: Storms and Resilience. As the Venus Accord was transmitted to Earth in the closing days of year 55, no one in the colony could have anticipated that nature itself would soon test their resolve far more severely than any political challenge. The 15 years that followed would become known as the Storm Era, a period when Venus's atmospheric dynamics underwent unprecedented changes that threatened the very existence of the floating habitats and forced the colonists to adapt in ways they had never imagined necessary. The first warning signs appeared in year 56, when atmospheric monitoring stations began detecting unusual wind pattern variations in Venus's middle cloud layers. The superrotation of Venus's atmosphere, the phenomenon where the entire atmosphere circles the planet in just 4 Earth days, much faster than the planet's own rotation, had been well documented since the earliest days of Venus exploration. However, the new data showed increasing variability in these patterns, with localized acceleration zones developing and dissipating unpredictably. Initially, these changes were treated as scientific curiosities rather than threats. Cloud Haven 4 adjusted its atmospheric ballast systems to compensate for the stronger wind currents during a particularly intense period, but this was considered routine operational adaptation. It wasn't until late in year 57 that the true magnitude of the atmospheric changes became apparent. On day 267 of that year, Cloud Haven 2 encountered what would later be classified as the first major event of the Great Cloud Disruption, a massive atmospheric disturbance that combined extreme vertical shear, unprecedented turbulence, and localized pressure variations far beyond the habitat's design parameters. For 27 terrifying hours, the habitat was subjected to forces that stressed its structure to the absolute limits of tolerance. When the disturbance finally passed, the damage assessment was sobering. Multiple exterior sensor arrays had been completely stripped away. 2 of the primary solar collection panels had suffered irreparable damage, and most concerning, stress fractures had developed in several secondary structural members. While the critical hull integrity remained intact thanks to the redundant safety systems implemented after the pressure cascade incident years earlier, the habitat had come dangerously close to catastrophic failure. In the months that followed, similar atmospheric disturbances affected other habitats, though none as severely as the initial event at Cloud Haven 2. Analysis of atmospheric data revealed that Venus was experiencing what appeared to be a planet-wide climate shift. The causes remained theoretical. Some researchers suggested subtle changes in solar output affecting Venus's already precarious greenhouse effect, while others proposed that the planet had entered a natural climatic cycle previously undetected by the relatively brief period of human observation. Regardless of the cause, the effects were undeniable and potentially catastrophic for the floating colony. By mid-year 58, the Administrative Council formally declared a colony-wide emergency, suspending normal operations and redirecting all available resources toward understanding and adapting to the changing atmospheric conditions. The period now known as the Great Cloud Disruption had officially begun. The first priority was developing better predictive capabilities. The existing atmospheric monitoring system, designed primarily for scientific research and routine navigational support, proved wholly inadequate for detecting and tracking the new, more violent storm systems. In response, the colony initiated the Weather Prediction Network project, the most extensive monitoring infrastructure ever deployed on Venus. The network design called for hundreds of autonomous sensor platforms distributed throughout Venus's atmosphere at multiple altitudes. Each platform carried instruments to measure wind speed, direction, pressure, temperature, and chemical composition, transmitting data in real time to a central processing facility established in Cloud Haven 3. Deployment began immediately, with manufacturing facilities operating continuously to produce the necessary equipment. By year 59, over 200 sensor platforms were operational, creating the first truly comprehensive picture of Venus's evolving atmospheric dynamics. The Visualization Center in Cloud Haven 3 displayed a three-dimensional representation of the entire atmospheric system, highlighting developing disturbances and projecting their likely paths and intensities. This early warning capability proved invaluable, giving habitats precious hours to prepare for approaching storms that might otherwise have caught them with minimal warning. The predictive algorithms developed during this period represented a significant advance in meteorological science. Traditional weather modeling developed for Earth proved inadequate for Venus's more complex atmospheric dynamics. The Venusian meteorologists pioneered new approaches that combined fluid dynamics modeling with machine learning systems that continuously refined their predictions based on observed outcomes. By year 62, the system could predict major disturbances up to 72 hours in advance with 85% accuracy, a remarkable achievement considering the complexity of the phenomena involved. While prediction improved the colony's ability to prepare for storms, it did nothing to enhance the habitat's physical resilience to the extreme conditions they now regularly encountered. This led to the Habitat Strengthening Initiative, a massive engineering project to upgrade all existing habitats to withstand the new atmospheric realities. The initiative began with a comprehensive structural assessment of each habitat, identifying potential failure points under various stress scenarios. Structural engineers developed reinforcement plans tailored to each habitat's specific design and condition, prioritizing critical systems and areas most vulnerable to the types of stresses observed during storm events. Implementation proved challenging, as major structural work had to be conducted while habitats remained fully operational. There was nowhere to relocate residents during construction. Work proceeded in carefully planned phases, with sections temporarily sealed off and depressurized to allow external reinforcement, then reintegrated into the habitat systems. The reinforcement materials themselves represented a new generation of composites developed specifically for the Strengthening Initiative. Drawing on the colony's growing manufacturing capabilities and materials science expertise, engineers created carbon-titanium hybrid structures with unprecedented strength-to-weight ratios. These materials, later referred to as storm-grade composites, became standard in all Venusian construction moving forward. Cloud Haven 5, still under construction when the Great Cloud Disruption began, underwent a complete redesign incorporating these new materials and structural approaches. Its completion was delayed by nearly 3 years, but the resulting habitat featured a revolutionary stress distribution system that allowed the entire structure to flex and adapt to atmospheric forces rather than rigidly resisting them. This design approach, inspired by Earth's tallest skyscrapers and their ability to sway during high winds, proved remarkably effective in the Venusian context. By year 64, all existing habitats had completed their strengthening modifications, and regular stress monitoring became part of standard operations throughout the colony. The effort had consumed enormous resources and delayed many planned expansions, but it ensured the physical survival of the habitats through even the most extreme conditions encountered during the Great Cloud Disruption. The atmospheric challenges coincided with another significant difficulty: disruption to the supply chain from Earth. The Venus Accord negotiations had eventually resulted in a compromise framework maintaining Earth support while granting greater colonial autonomy in internal matters. However, implementation of this new arrangement was complicated by a period of unusually high solar activity beginning in year 60. The increased solar activity created hazardous radiation conditions, along the Earth-Venus transit route during certain periods, requiring supply missions to be rescheduled to avoid the most dangerous intervals. Additionally, the optimal launch windows for efficient transit between the planets were sometimes rendered unusable by solar conditions, forcing missions to use less efficient trajectories that increased transit time and reduced payload capacity. The combined effect was a significant reduction in the frequency and volume of Earth supply deliveries precisely when the colony faced its greatest challenges from the atmospheric disruptions. Critical components for habitat strengthening and replacement parts for storm-damaged systems faced delays of months or even years, forcing the colonists to develop alternative solutions using locally available resources. This period of forced self-reliance accelerated the colony's manufacturing capabilities in unexpected ways. The Helios processing platform, originally designed primarily for silicon production, expanded its operations to include a wider range of materials and components. Engineers developed innovative substitutes for Earth-sourced components, often creating Venus-specific designs that actually outperformed the original items in the colony's unique environment. The supply limitations also drove advances in recycling and resource recovery. The Materials Reclamation Program, initiated in year 62, established sophisticated processing facilities to extract usable materials from damaged equipment and structures. These facilities could separate and purify various metals, composites, and rare elements at an efficiency approaching 95%, creating a closed-loop material system within the colony that reduced dependence on both Earth supplies and surface mining operations, which had been curtailed due to the atmospheric conditions. Perhaps the most significant innovation emerging from this period of challenge was the development of the nomad habitats. Traditional habitats, even with strengthening modifications, remained vulnerable to the most extreme atmospheric events simply due to their size and relative immobility. While they could make adjustments to their altitude and had limited propulsion capabilities, they could not rapidly relocate to avoid developing storm systems. The nomad concept proposed a fundamentally different approach: smaller, highly maneuverable habitats specifically designed to navigate between storm systems rather than weathering them in place. The first prototype, Nomad Alpha, was deployed in year 63 as a research platform to test the concept's viability. Nomad Alpha was approximately 1/10 the size of a standard habitat, with a highly streamlined profile and powerful electric propulsion systems that gave it unprecedented maneuverability within Venus's atmosphere. Its navigation systems were directly integrated with the weather prediction network, allowing it to continuously adjust its course based on real-time atmospheric data and forecasts. The prototype demonstrated remarkable capability to maintain position in relatively calm atmospheric regions despite the increasingly chaotic general conditions. It could detect approaching disturbances and rapidly relocate to safer areas, sometimes traveling hundreds of kilometers in a single day, a level of mobility previously unimaginable for Venus habitats. Following Alpha's success, 5 additional nomad habitats were constructed and deployed over the next 3 years. While too small to house large populations, they served critical functions as mobile research platforms, emergency response bases, and crucial links in the colony's increasingly distributed infrastructure. Nomad Gamma, specifically outfitted as a medical facility, saved numerous lives by rapidly deploying to habitats damaged during severe storm events, providing specialized care that would otherwise have been unavailable. The nomads also pioneered new approaches to habitat propulsion that would eventually influence the larger habitats. Their advanced directional thrust systems, more sophisticated than the basic positioning fans of the original habitats, demonstrated the potential for greater controlled mobility even for larger structures. By year 67, both Cloud Haven 3 and 5 had implemented modified versions of these systems, giving them enhanced ability to actively navigate within Venus's atmosphere rather than merely adjusting their passive drift. Throughout this period of intense challenge, the colonists displayed remarkable resilience and adaptability. Community support systems evolved to help those most affected by storm damage or supply limitations. Resource sharing became an ingrained cultural value, with informal exchange networks ensuring that critical needs were met throughout the colony, regardless of official distribution channels. The psychological impact of the Great Cloud Disruption was significant. Living with the constant threat of catastrophic storms created a background stress that affected every aspect of colony life. Mental health specialists developed specific interventions for what they termed atmospheric anxiety, the chronic stress response to the unpredictable environment. Community gathering spaces were redesigned to minimize external visibility during storms, creating psychological safe zones where colonists could temporarily escape awareness of the threats outside. Yet alongside these challenges emerged a deepened sense of community identity and pride. The shared experience of surviving and adapting to the Great Cloud Disruption created bonds that transcended previous political and social divisions. The Venus-born generation, in particular, embraced the challenge as formative to their identity. They were not merely people who happened to live on Venus, but Venusians, shaped by their world's harsh realities and equal to its challenges. By year 68, atmospheric data suggested that the most severe phase of the Great Cloud Disruption was beginning to abate. Storm frequency and intensity showed measurable decreases, and longer periods of relative stability allowed for recovery operations and the resumption of some development projects that had been suspended during the crisis years. As conditions gradually improved, the colony took stock of what they had endured and achieved. Not a single habitat had been lost despite conditions far more extreme than anything anticipated in their original design parameters. The prediction and response systems developed during the crisis had created an unprecedented understanding of Venus's atmospheric dynamics. Most importantly, the colony had become more self-sufficient, resilient, and unified through the shared experience of meeting an existential threat. When regular communication and supply missions from Earth fully resumed in year 69, the reports and data transmitted back transformed humanity's perception of the Venus colony. What had been viewed by many on Earth as an expensive, fragile outpost constantly at the mercy of its hostile environment was now recognized as perhaps the most resilient human settlement ever established. The Triumph Through Adaptation documentary, compiled from footage recorded throughout the storm era and broadcast globally on Earth in year 70, captured this transformation in public perception. The images of habitats engulfed in swirling, violent cloud formations yet maintaining operations, of repair crews working in specialized pressure suits to fix external damage during storm intervals, and of agricultural modules producing food despite reduced external solar input, showcased a level of human adaptability that inspired audiences worldwide. Perhaps most powerful were the interviews with colonists, particularly those born on Venus who had never known any other home. Their matter-of-fact descriptions of storm preparations and adaptation strategies delivered without the sense of extraordinary effort that Earth viewers perceived, demonstrated how thoroughly they had integrated the challenges of their environment into their understanding of normal life. The documentary's closing sequence, showing the deployment of the first post-crisis expansion habitat, Cloud Haven 6, against the backdrop of Venus's still turbulent but manageable atmosphere, became an iconic image symbolizing humanity's capacity to adapt and thrive even in the most challenging environments the solar system could present. As the Venus colony entered its 7th decade, it had been transformed by the Great Cloud Disruption in ways that extended far beyond the physical strengthening of its habitats or the advancement of its predictive capabilities. The colonists had developed not just technologies, but cultural and psychological tools for resilience that would serve them through future challenges. They had proven to themselves and to watching humanity on Earth that their cloud-born civilization was not a fragile experiment, but a durable extension of human society into one of the most unlikely habitats imaginable. The coming decades would bring new challenges and opportunities, but the foundation laid during the storm era, both the physical infrastructure and the resilient community identity, provided a solid base for continued growth and development. Venus's atmosphere remained hostile by Earth standards, but the colonists had demonstrated conclusively that with ingenuity, adaptability, and collective determination, humanity could make a home even among the tempestuous clouds of our sister planet. Part 7: Scientific Renaissance. The resolution of the Great Cloud Disruption marked not merely the end of a crisis, but the beginning of a new era for the Venus colony. Having survived and adapted to atmospheric challenges far beyond their original design parameters, the colonists emerged with renewed confidence, advanced technologies, and a deeper understanding of their adopted world. The next 15 years would see this hard-won knowledge transformed into a period of extraordinary scientific advancement, a true renaissance of discovery and innovation that would reshape humanity's understanding not just of Venus, but of planetary science throughout the solar system. The foundation for this scientific flowering was established in year 71 with the creation of Venus Research University, or VRU, the first dedicated higher education institution beyond Earth. While educational programs had existed within the colony since its early years, these had primarily focused on practical training and skills transmission necessary for colony operations. VRU represented something far more ambitious, a comprehensive research university dedicated to advancing knowledge across multiple disciplines, with Venus itself as the primary laboratory. The university was established in a dedicated section of Cloud Haven 6, the newest and most technologically advanced habitat. Its physical design reflected its mission of knowledge creation and dissemination, with flexible research spaces, collaborative commons areas, and technical facilities purpose-built for Venusian science. Perhaps most striking was the Grand Observatory, a multi-level viewing gallery with specialized instruments that allowed direct observation and analysis of Venus's atmospheric phenomena from within the safety of the habitat. VRU's organizational structure broke with Earth academic traditions in several important ways. Rather than dividing into traditional departments based on historical disciplinary boundaries, the university organized around 5 integrated research institutes: atmospheric sciences, extreme environment engineering, biological adaptation, planetary systems, and human factors. This structure encouraged cross-disciplinary collaboration and reflected the interconnected nature of challenges and opportunities in the Venusian context. The university's founding faculty included both experienced researchers who had been part of the colony for decades and newly arrived specialists from Earth, creating a blend of deep Venusian experience and fresh perspectives. Importantly, the first class of students included a significant number of Venus-born colonists who had completed their preliminary education within the colony and now sought advanced training tailored to their unique environment. From its inception, VRU established formal research partnerships with major Earth universities, creating exchange programs for both faculty and students. These exchanges brought Earth-based researchers to Venus for extended periods, allowing them to conduct studies impossible anywhere else, while giving Venusian scholars opportunities to share their unique perspectives and findings with the broader scientific community. The university quickly became the intellectual heart of the colony, stimulating advances across multiple fields simultaneously. Among the most significant early breakthroughs were in climate modeling, an area where Venus provided unparalleled opportunities for study. The atmospheric monitoring infrastructure developed during the Great Cloud Disruption had generated the most comprehensive dataset ever assembled on a planetary climate system other than Earth's. This data, combined with the computational resources at VRU and the expertise of researchers who had lived through the atmospheric disruptions, created ideal conditions for revolutionary advances in climate science. The Venus Global Climate Model, unveiled in year 73, represented a quantum leap in planetary climate simulation capabilities. Unlike previous models that relied heavily on Earth-based assumptions, this system was built from first principles specifically for Venus conditions, incorporating the full complexity of the planet's unique atmospheric chemistry, cloud dynamics, and energy transfer mechanisms. The model's predictive power was demonstrated dramatically when it accurately forecast a series of regional atmospheric disturbances 6 months before they developed, a level of long-term prediction that exceeded capabilities even for Earth's climate system at that time. This validation established VRU as the leading center for planetary climate research in the solar system and created immediate applications for colony operations, allowing far more efficient planning and resource allocation based on anticipated atmospheric conditions. As the modeling techniques matured, researchers began applying the core methodologies to other planetary atmospheres. The Comparative Planetary Climate Initiative, launched in year 75, adapted the Venus model framework to simulate atmospheric systems on Mars, Titan, and gas giants like Jupiter. This work revealed previously unrecognized commonalities in how planetary atmospheres function despite their dramatic differences in composition and conditions. These insights proved particularly valuable for Earth climate science. The extreme case of Venus, with its runaway greenhouse effect and complex atmospheric chemistry, provided a unique laboratory for understanding climate feedback mechanisms that were relevant to Earth's increasing carbon dioxide levels. Several key refinements to Earth climate models incorporated principles first identified in the Venus simulations, improving the accuracy of terrestrial climate predictions at a crucial time in Earth's environmental history. While atmospheric research flourished in the clouds, another major scientific initiative focused on the still largely unexplored surface below. Despite decades of robotic missions and material extraction operations, direct scientific study of Venus's surface remained limited by the extreme conditions. The autonomous systems could gather samples and conduct basic analysis, but many research questions required more sophisticated investigation than robots could provide. In year 76, after 5 years of intensive development, the colony achieved a historic milestone with the deployment of Surface Laboratory 1, the first facility on Venus's surface designed for direct human operation, albeit for limited durations. Located on a plateau in the Maxwell Montes region, where conditions were marginally less extreme than the lowlands, the laboratory represented the culmination of decades of advances in high-temperature materials and cooling technology. The facility's core was a pressurized module with multi-layered thermal protection systems unlike anything previously developed. The outer shell utilized reflective ceramics that rejected a significant portion of ambient heat, while the next layer incorporated phase-change cooling materials that absorbed heat through controlled melting processes. The innermost layer featured active cooling systems using closed-loop refrigeration cycles specifically engineered for Venus's extreme temperature gradient. Inside this protective cocoon, conditions could be maintained at temperatures and pressures suitable for human occupancy for up to 72 hours before the cooling systems required regeneration. A brief window, but revolutionary considering the 462 degrees Celsius inferno outside. Access to the facility was provided by a specially designed descent vehicle that could transport researchers from the floating habitats to the surface and back, with each mission lasting approximately 1 week, including transit time. The scientific returns from direct human presence on the surface proved immense. Researchers could perform complex experimental procedures, make real-time observational decisions, and utilize sophisticated instruments that were too delicate or complex for fully autonomous operation. The first geology team to utilize the facility discovered evidence of past water activity preserved in rock formations that had been overlooked by robotic samplers, opening new chapters in understanding Venus's ancient history. Surface Laboratory 1 also enabled the installation of long-term monitoring equipment that significantly expanded knowledge of Venus's geological activities. Seismometers detected previously unknown patterns of tectonic movement, suggesting that Venus, while lacking Earth-style plate tectonics, experienced more geological activity than previously recognized. These findings prompted a fundamental reassessment of comparative planetary geology throughout the inner solar system. By year 80, 3 additional surface laboratories had been established in different geological regions, creating a network of research outposts that supported rotating teams of scientists. While each visit remained brief, the cumulative knowledge generated transformed understanding of Venus's surface environment and history. Perhaps most significantly, evidence mounted that Venus had experienced Earth-like conditions for billions of years before its catastrophic greenhouse transformation, a sobering case study in planetary climate evolution with obvious implications for Earth's future. As surface and atmospheric research expanded understanding of Venus's physical systems, another branch of scientific inquiry focused on the biological implications of the Venusian environment. The Biological Adaptation Research Institute at VRU pioneered work in understanding how terrestrial life might be modified to better survive in the unique conditions of the Venus colony, and potentially in Venus's atmosphere itself. The practical applications of this research were immediate and significant for the colony. Genetically modified food crops developed specifically for Venusian conditions increased agricultural yields by as much as 40% compared to their Earth-originated ancestors. These modifications included enhanced ability to photosynthesize under the filtered golden light conditions within the habitats, improved growth under the slightly higher gravity of Venus, 0.9 gravity compared to Earth's 1 gravity, and optimized water usage suited to the colony's careful water management systems. More ambitious were the efforts to develop microorganisms that could process Venus's atmospheric carbon dioxide more efficiently than mechanical systems. The Carbon Capture Microbe Project, initiated in year 77, genetically engineered cyanobacteria to thrive in sealed exterior cultivation chambers attached to habitat exteriors. These microorganisms absorbed carbon dioxide through semi-permeable membranes and produced oxygen at rates significantly higher than mechanical carbon dioxide electrolysis, while requiring far less energy input. By year 82, these biological air processing systems supplemented mechanical systems throughout the colony, improving efficiency and resilience of life support infrastructure. The success of these controlled exterior applications led to more controversial proposals that would directly engage with Venus's native environment in ways never before attempted. The Acid Ecosystem Project, launched in year 83, represented the most ambitious biological engineering effort in human history to that point. The project aimed to develop microorganisms capable of surviving directly in Venus's cloud layers, specifically in the upper atmosphere region around 55 to 60 kilometers altitude, where temperature and pressure were relatively moderate, but the highly acidic conditions prevented any known Earth life from surviving. The project combined cutting-edge genetic engineering with lessons learned from Earth's most extreme acidophile organisms, microbes that thrived in highly acidic environments like volcanic hot springs or acid mine drainage. Through careful modification of protective cell membranes and internal pH regulation systems, researchers developed candidate organisms theoretically capable of metabolizing in Venus's sulfuric acid clouds. Initial testing occurred in simulation chambers that perfectly replicated upper Venusian atmospheric conditions. When several microbial strains demonstrated sustained survival and reproduction in these controlled environments, the project proposed the next logical step: limited release of these organisms into Venus's actual atmosphere to assess their viability in genuinely native conditions. This proposal triggered intense debate throughout the scientific community, both on Venus and Earth. Proponents argued that the introduction of these engineered microbes could provide valuable scientific insights, while potentially beginning beneficial processes like oxygen production in Venus's atmosphere. Critics countered that deliberately introducing Earth-derived organisms to another planetary environment crossed a critical ethical boundary in planetary protection, potentially contaminating Venus in ways that could complicate future scientific study or have unforeseen consequences. The debate reached the highest levels of colony governance, with the Venusian Atmospheric Administrative Council ultimately deciding to proceed with extremely limited, carefully monitored test releases. In year 85, the first such release occurred, with a small population of engineered microbes introduced into a contained section of atmosphere using a specialized drone platform. Monitoring equipment tracked the organism's survival and distribution, confirming that some strains could indeed survive for limited periods in Venus's clouds before succumbing to the extreme acidity. While no strain achieved permanent establishment in this first test, the partial success provided valuable data for further refinement and established the principle that Earth-derived life, with sufficient adaptation, might eventually exist in Venus's upper atmosphere. The Acid Ecosystem Project remained controversial, but it represented a bold new frontier in humanity's relationship with other worlds, moving beyond mere observation or resource extraction to the deliberate attempt to extend the reach of Earth's biosphere, however modestly, into extraterrestrial environments. The philosophical and ethical discussions sparked by these experiments would continue for decades, influencing humanity's approach to other worlds throughout the solar system. While biological research captured public attention with its dramatic implications, equally significant discoveries were emerging from a less glamorous but technically innovative program focused on Venus's dark side, the hemisphere experiencing night during the planet's slow rotation. Unlike Earth with its 24-hour day-night cycle, Venus's rotation is so slow that a complete day-night cycle takes 116.75 Earth days, creating extended dark periods unlike anything experienced on our home planet. The Night Side Survey, initiated in year 80, deployed a constellation of specialized sensing platforms equipped with advanced thermal imaging, radar, gravimetric sensors, and atmospheric composition analyzers. These platforms maintained fixed positions relative to Venus's surface rotation, using the improved propulsion systems developed during the storm era, allowing continuous monitoring of specific regions through their transition from day to night and back again. The survey revealed previously undetected phenomena unique to Venus's night side. Most dramatically, the thermal imaging equipment detected distinct patterns of infrared emission that varied by region and evolved over time, evidence of significant heat flow from Venus's interior that manifested differently across the surface. These patterns, invisible during the day due to overwhelming solar heating, provided new insights into Venus's internal structure and volcanic processes. Atmospheric sensors identified chemical reactions that occurred only in darkness, particularly involving sulfur compounds in the lower atmosphere. These reactions created unique cloud structures and precipitation events that had never been observed during daytime studies. The discovery of these diurnal chemical cycles revolutionized understanding of Venus's atmospheric chemistry and explained several long-standing puzzles about observed variations in cloud composition. Perhaps most unexpected were the electrical phenomena documented by the survey. Venus's night side exhibited complex patterns of electrical activity, including massive lightning discharges far more powerful than those on Earth. These electrical storms followed predictable patterns related to the Terminator line, the moving boundary between day and night sides, creating what researchers termed electrical weather that influenced atmospheric circulation and chemistry. The comprehensive data from the Night Side Survey compiled into the Venus Complete Model, the first truly global understanding of a planetary system beyond Earth that incorporated both day and night processes and their interactions. This holistic view revealed Venus as a far more dynamic, complex world than previously understood, with interdependent systems that could only be fully comprehended by considering the planet as an integrated whole rather than studying isolated components. By year 85, the scientific renaissance had transformed humanity's understanding not just of Venus, but of planetary science broadly. The unique observational position of living within Venus's atmosphere, combined with the technological capabilities developed during the crisis years, and the institutional framework of Venus Research University, had created an unprecedented platform for scientific advancement. The period also witnessed a transformation in how colonists perceived their relationship with Venus. The early years of colonization had necessarily focused on survival, adapting human systems to function despite Venus's hostile environment. The scientific renaissance shifted this perspective, encouraging deeper understanding of Venus as a complex planetary system, worthy of study in its own right, rather than merely an environment to be endured or exploited. This evolving relationship was perhaps best expressed in the Venus Charter revision of year 84, which formally recognized the colony's responsibility for stewardship of Venus's natural systems through scientific understanding and ethical engagement. This principle, articulated by a community now spanning multiple generations of Venus residents, reflected a maturing perspective that balanced human needs with respect for the integrity of the planetary environment that had become their home. The scientific achievements of this period extended far beyond Venus itself, influencing understanding of planetary processes throughout the solar system and preparing humanity for further steps in space exploration and settlement. The technologies, methodologies, and philosophical approaches developed during Venus's scientific renaissance would prove invaluable as humanity continued its expansion to other worlds, carrying forward lessons learned in the clouds of our nearest planetary neighbor. As the Venus colony prepared to enter its 9th decade, it had evolved from a precarious outpost to a thriving center of scientific excellence recognized throughout human civilization. The knowledge generated during these years of discovery would provide the foundation for the next phase of Venusian development, a period of unprecedented population growth and social evolution that would test the colony's capacity in entirely new ways. Part 8: Population Boom. The scientific achievements of Venus's Renaissance period fundamentally altered perceptions of the colony, both within and beyond its atmospheric bounds. What had begun as a daring outpost of scientific research evolved into a resilient community during the storm era and blossomed into a center of innovation during the scientific renaissance, now faced an unprecedented development, becoming a desirable destination for large-scale migration from Earth. The years from 85 to 100 would see the Venus colony transform from specialized community to genuine society through a population explosion that would test both its physical infrastructure and cultural identity. The catalyst for this dramatic demographic shift came from an unexpected source: Earth's own environmental challenges. By the mid-80s of the Venus colony timeline, Earth was experiencing increasingly severe climate instability, resource competition, and the social tensions that accompanied these pressures. The technologies and knowledge developed on Venus, particularly in closed-system resource management, atmospheric science, and sustainable living in controlled environments, suddenly held tremendous relevance for Earth's difficulties. This created a new perception of Venus among Earth's population. What had once been viewed as an exotic scientific endeavor or a testament to human endurance was increasingly seen as a model for sustainable living and a potential alternative to Earth's mounting problems. Applications for migration to Venus, which had maintained a steady but modest flow throughout the colony's history, surged dramatically beginning in year 86, creating what historians would later call the second wave of Venusian settlement. Unlike the first wave of colonists, who had been primarily scientists, engineers, and specialists selected specifically for the Venus mission, the second wave applicants came from diverse backgrounds: educators, medical professionals, artists, entrepreneurs, and families seeking a fresh start in what was increasingly portrayed in Earth media as a society of innovation and opportunity. While selection still prioritized skills relevant to the colony's needs, The criteria broadened significantly to accommodate this wider pool of potential colonists. The Venus Colonial Authority, which had replaced the earlier Administrative Council following the Venus Accord negotiations, initially approached this surge with caution. The colony's resources and infrastructure had been carefully scaled for gradual growth, not a sudden population influx. However, the scientific and industrial advances of the previous decade had created significant capacity for expansion, particularly in food production, atmospheric processing, and habitat construction using Venus-sourced materials. After extensive debate, the authority approved an accelerated growth plan in year 87, establishing a target of tripling the colony's population over the next 15 years. This ambitious goal would require not just expanded habitats, but a fundamental reimagining of the colony's physical and social organization. The centerpiece of this expansion was the Cloud Haven Metropolis concept, a plan to physically connect multiple existing habitats into an integrated urban environment, rather than continuing the previous model of separate habitats linked by transportation systems. The engineering challenges were formidable, requiring structural connections that could accommodate the subtle but constant movements of each habitat in Venus's atmospheric currents. The solution came in the form of flexible megastructural connectors, enormous carbon composite tubes with multiple internal layers that could extend, contract, and bend within carefully calculated tolerances. These connectors, nicknamed accordions for their ability to flex with atmospheric movements, contained both pressurized transit corridors and utility conduits carrying water, electrical power, and data between habitats. Construction of the first connector between Cloud Haven 3 and Cloud Haven 6 began in year 88, with teams working simultaneously from both habitats. The precision required was extraordinary. Aligning massive structures floating in Venus's atmosphere required continuous adjustment and real-time monitoring. When the final section was secured in place after 7 months of construction, the moment was celebrated throughout the colony as the birth of a genuine city among the clouds. The successful connection created a combined urban area with nearly twice the interior volume of any previous individual habitat. More importantly, it allowed specialization of functions between connected habitats. Cloud Haven 6 expanded its residential sections, while Cloud Haven 3 repurposed space for manufacturing and commercial activities. This specialization created efficiencies that would become crucial as the population grew. Over the next 5 years, additional connectors joined Cloud Haven 4 and later Cloud Haven 5 to the growing metropolis. Each connection increased not just the physical space, but the operational flexibility of the colony, allowing resources, people, and materials to flow more efficiently between previously separate environments. By year 93, 4 of the major habitats had been incorporated into what was now officially designated Cloud Haven Metropolis, the first true city beyond Earth. The metropolis design incorporated lessons from both Earth urban planning and the unique requirements of Venusian life. Public spaces were created at connector junctions, becoming vibrant community centers where colonists from different habitats mingled and exchanged ideas. Vertical transportation systems allowed efficient movement between levels, while automated delivery networks transported goods and materials throughout the connected structure. Perhaps most striking were the Vista Commons, large, multi-level public areas with reinforced viewports providing panoramic views of Venus's cloud landscapes. These spaces became the signature feature of the metropolis, hosting everything from formal ceremonies to casual gatherings with Venus's golden clouds as a backdrop. The largest of these, the Grand Concourse in the connector between Cloud Haven 3 and 6, could accommodate nearly 1,000 people, a scale of public gathering unprecedented in the colony's previous history. As the physical infrastructure expanded, the population grew accordingly. Transport ships from Earth arrived on regular schedules, each bringing new colonists who had completed the extensive training program required for Venusian adaptation. By year 95, the population had reached nearly 5,000, more than double the pre-expansion number, and continued to grow steadily as additional habitats joined the metropolis and new standalone habitats were constructed. This population growth brought unprecedented diversity to Venus. The second wave included people from all of Earth's cultures and backgrounds, bringing with them traditions, perspectives, and expertise that enriched colony life. Culinary traditions diversified as new arrivals adapted their native cooking techniques to available Venusian ingredients. The arts flourished with the influx of musicians, visual artists, and performers who created works specifically responsive to the Venusian environment. The economic structure diversified as well. While scientific research, agriculture, and manufacturing remained central to the colony's function, new enterprises emerged to serve the growing population. The first genuine markets appeared, where colonists could exchange goods and services outside the previous centrally managed distribution system. Specialized businesses developed to meet needs ranging from personal services to entertainment to custom manufacturing. This diversification created both opportunities and tensions. The original colonist families, many now in their second or third generation on Venus, sometimes found the rapid changes disorienting. Cultural practices that had evolved specifically for Venusian conditions occasionally clashed with Earth traditions brought by new arrivals. Economic disparities emerged between established colonists, with their deep integration into Venus systems and newcomers still finding their place. Navigating these changes required careful attention to social cohesion. The colonial authority established integration programs to help new arrivals adapt to Venusian norms, while encouraging established colonists to welcome the contributions newcomers brought. Community forums provided spaces for addressing tensions before they escalated, while mixed housing arrangements prevented the development of segregated enclaves based on Earth origin or arrival date. These efforts were largely successful in creating a cohesive society, but they couldn't completely eliminate the emergence of what came to be known as the identity question, the ongoing philosophical and practical debate about what it meant to be Venusian in this new, expanded colony. At the center of this question was the unique perspective of the first fully mature generation born on Venus. By the 90s, the earliest Venus-born children had reached adulthood and were starting families of their own. These native Venusians had never experienced Earth directly and related to it very differently than either first-wave colonists or recent arrivals. Physiological studies conducted by Venus Research University revealed subtle but significant adaptations in this Venus-born generation. Their cardiovascular systems showed enhanced efficiency in the colony's slightly higher gravity environment. Their visual processing was optimized for the filtered golden light that permeated the habitats. Most notably, their circadian rhythms had naturally adapted to Venus's 4-day atmospheric cycle rather than Earth's 24-hour day, giving them biological synchronization with their adopted world that Earth-born colonists never fully achieved even after years of residence. These physical adaptations were matched by psychological and cultural differences. Venus-born colonists exhibited distinctive thought patterns when solving spatial problems, reflecting their upbringing in the three-dimensional environment of the floating habitats rather than on a planetary surface. Their perception of distance and geography differed fundamentally from Earth norms, with up and down carrying different connotations when one's home is suspended in an atmosphere rather than built on solid ground. The educational system had evolved to accommodate these differences while still providing connection to Earth heritage. The Venusian educational framework, formalized in year 91, balanced Earth-originated knowledge with Venus-specific content through what educators called dual-context learning. Students studied Earth geography and ecosystems through immersive virtual reality since they couldn't experience them directly, while receiving hands-on education in Venusian atmospheric science and habitat engineering that would be impossible on Earth. This educational approach extended beyond basic knowledge to cultural literacy. Venus-born children learned Earth cultural references and history to communicate effectively with Earth-born colonists and maintain connection to humanity's original home. Simultaneously, they developed their own cultural frameworks and references specifically relevant to Venusian life, creating a genuine bicultural perspective that bridged their physical home and their ancestral heritage. The question of identity became explicitly political in year 97, when a group of Venus-born young adults formed the Venusian Heritage Association. This organization advocated for formal recognition of Venusian cultural distinctiveness and greater representation in colony governance for the perspectives of those born on Venus. While not seeking separation from Earth or rejection of new arrivals, they argued that the experiences and needs of Venus-born citizens required specific consideration in planning for the colony's future. The ensuing debates touched on fundamental questions of human identity in space. Was Venus simply an outpost of Earth civilization, or the beginning of a genuinely new branch of human society? Should Venusian culture strive to maintain maximum compatibility with Earth norms, or develop its own distinct values and practices optimized for its unique environment? How should the colony balance honoring its Earth origins with the emerging identity of a society that increasingly saw Venus as simply home? These philosophical questions played out against the practical backdrop of resource management for a rapidly growing population. Despite advanced recycling systems, expanded agricultural capacity, and increasingly efficient atmospheric processing, the population boom created significant strain on the colony's resource systems. Water remained the most challenging resource despite decades of improvements in acid-to-water conversion technology. The colony's water recycling systems operated at nearly 99% efficiency, but each new resident still required an initial water allocation, and the cumulative effect of thousands of new colonists created unprecedented demand. Conservation measures were strengthened, with water usage strictly monitored and innovative water-saving technologies implemented throughout the metropolis. Food production expanded through the creation of specialized agricultural habitats optimized solely for intensive farming. These habitats, connected to the metropolis by regular transport ships rather than physical connectors, maximized food production per cubic meter through advanced vertical farming techniques, controlled lighting, and crop varieties specifically bred for maximum yield in Venusian conditions. By year 99, these agricultural outposts were producing sufficient nutrition for the entire colony population, though with less variety than many Earth-born colonists were accustomed to. Energy demands increased dramatically with the growing population and expanded manufacturing. The existing solar collection platforms were supplemented with a new generation of energy systems that tapped into Venus's powerful atmospheric currents. Wind turbines designed specifically for the intense, consistent winds of Venus's upper atmosphere were deployed in arrays surrounding the habitats, capturing kinetic energy that previously had been merely an operational challenge to be overcome. The most significant resource challenge came in living space itself. Even with the expanded metropolis and new habitats under construction, residential areas became increasingly crowded as population growth occasionally outpaced construction capacity. The colony implemented a dynamic allocation system that assigned living space based on both family size and community contribution, ensuring efficient use of the limited volume available. These resource pressures led to the most significant government reorganization since the Venus Accord. In year 98, the Resource Management Council was established with representation from all major habitats and demographic groups. The council received authority to set colony-wide resource policies, allocate materials for construction and manufacturing, and establish conservation requirements during shortage periods. This centralized approach to resource management created tensions with the increasingly diverse and entrepreneurial colony society. Small businesses and private initiatives sometimes found their plans delayed by council allocation decisions, while individuals accustomed to Earth's less constrained resource environment chafed at conservation requirements. Yet most colonists recognized the necessity of careful resource stewardship in their closed environmental system, accepting temporary limitations in exchange for long-term sustainability. The population boom culminated in year 100 with the colony centennial celebration, a year-long series of events commemorating the 100-year mark since the first deployment of Cloud Haven 1. The centerpiece of these celebrations was the completion of Cloud Haven Metropolis with the connection of the final major habitat, creating a unified urban structure housing over 8,000 residents, the largest human settlement beyond Earth. The centennial prompted reflection on how far the colony had come and serious consideration of its future direction. Historical exhibitions traced the journey from experimental outpost to thriving city, highlighting both the technical achievements and the human stories that had shaped the colony's development. Symposia at Venus Research University explored potential futures for Venus settlement, including ambitious proposals for surface facilities and atmospheric modification that would have seemed like fantasy in the colony's early years. Most powerfully, the centennial featured intergenerational dialogues between first-wave colonists, now elderly but still present in the community, and the youngest Venus-born children. These conversations, recorded for posterity, captured the extraordinary perspective of those who had experienced the entire arc of Venus colonization, alongside those who knew only the thriving Cloud City as their reality. The contrasts and continuities in their experiences provided perhaps the clearest picture of how thoroughly human presence had become established in Venus's atmosphere. As the Venus colony entered its second century, it had transformed from humanity's most ambitious experiment into a genuine society with its own identity, culture, and future trajectory. The population boom had stressed systems and raised challenging questions, but it had also created the critical mass necessary for a self-sustaining human presence that no longer felt experimental or temporary. The floating city among Venus's clouds, now home to multiple generations who had never known any other world, stood as testament to humanity's adaptive capacity and determination to expand beyond its original planetary home. Though challenges remained and tensions between Earth and Venusian identities would continue to evolve, the fundamental question of whether humans could truly make a home in Venus's atmosphere had been definitively answered. The cloud civilization had moved beyond mere survival to genuine flourishing, creating a unique branch of human culture adapted to one of the most unlikely habitats in the solar system. Part 9: Industrial Revolution. As Venus entered its second century of human habitation, the foundations laid during the population boom created the conditions for a transformation as significant as the Industrial Revolution on Earth centuries earlier. The growing population, diversified skill base, and enhanced resource access combined to shift the colony from a primarily self-sustaining scientific settlement to a genuine industrial power in the solar system. Years 100 through 115 marked Venus's Industrial Revolution, a period when manufacturing capabilities, economic systems, and interplanetary relationships fundamentally evolved. The groundwork for this industrial expansion had been developing for decades. The surface mining operations initiated during the Mining Challenge period had steadily improved in efficiency and scope, providing increasing quantities of metals and minerals. The processing platforms had refined their techniques for converting these raw materials into usable forms under Venusian conditions. Most importantly, the knowledge base accumulated at Venus Research University and throughout the colony's manufacturing sectors had created a reservoir of Venus-specific industrial expertise unavailable anywhere else in the solar system. In year 101, the colonial authority approved the Industrial Capacity Expansion Plan, an ambitious 15-year initiative to transform the colony's manufacturing capabilities. The plan called for dedicated industrial habitats separate from but connected to the primary residential areas, allowing for specialized environments optimized for production rather than human comfort. The first of these, Production Platform Alpha, began construction in year 102. Unlike the main habitats with their balanced focus on living space, agriculture, and mixed-use areas, Alpha was designed exclusively for efficient manufacturing. Its interior was arranged in concentric production rings surrounding a central materials handling hub, with automated transport systems moving components and finished goods throughout the structure. Environmental controls maintained optimal conditions for various manufacturing processes rather than human preferences, with personnel wearing specialized equipment when working in sections with non-standard temperature, lighting, or atmospheric composition. Alpha became operational in year 104, focusing initially on habitat components and life support systems, high-volume necessities for the growing colony. Its production lines utilized advanced automation developed specifically for Venusian conditions, with robotic systems handling repetitive tasks while human workers focused on oversight, quality control, and process improvement. This combination proved remarkably effective, achieving production efficiencies that rivaled Earth's most advanced factories despite the challenges of operating in Venus's atmosphere. The success of Production Platform Alpha led to rapid development of additional specialized manufacturing habitats. Beta, completed in year 106, focused on electronic components and control systems, reducing the colony's dependence on Earth imports for its most sophisticated technology needs. Gamma, operational by year 108, specialized in chemical processing and materials science, producing everything from pharmaceuticals to advanced composites using Venus-sourced precursors. Each of these platforms incorporated lessons learned from its predecessors, creating an increasingly efficient industrial network. The modularity of their design allowed for rapid reconfiguration as production needs evolved, while standardized interfaces ensured smooth integration with the colony's logistics systems. By year 110, 7 specialized production platforms were operational, creating a manufacturing base far beyond anything previously possible in space environments. This manufacturing expansion enabled the colony's most ambitious industrial project to date, the Venus Orbital Construction Facility, commonly known as the floating shipyards. Initiated in year 105, this project aimed to establish Venus's capacity to construct spacecraft and large-scale space structures using primarily locally sourced materials rather than components imported from Earth. The logistics were formidable. While the colony had established extensive surface mining operations, transporting large quantities of materials from surface to orbit required new approaches. The solution combined 2 technologies: enhanced versions of the surface ascent vehicles that had been used for smaller-scale transport, and a revolutionary mass driver system installed on one of Venus's highest mountain peaks. The mass driver, essentially an electromagnetic catapult, could launch dense, raw materials packages to high altitude where they were captured by specialized collection vessels. This system dramatically reduced the energy requirements for orbit transfer compared to conventional rocket launches from surface to space. For materials that couldn't withstand the acceleration forces of the mass driver, the enhanced surface ascent vehicles provided a gentler but more energy-intensive alternative. The orbital facility itself took shape gradually as modules were constructed in the manufacturing habitats, transported to orbit, and assembled by construction teams working in Venus orbit. Unlike Earth orbital facilities, which relied heavily on components manufactured on the planetary surface, Venus's floating shipyards incorporated on-site manufacturing capabilities that could process raw materials into finished components in the orbital environment itself. This approach created unique advantages. The microgravity environment allowed for manufacturing processes impossible in Venus's habitats with their Earth-like gravity. Structures could be built that would collapse under their own weight in gravity, but functioned perfectly in orbit. The absence of atmospheric contaminants enabled production of ultra-pure materials for electronics and optical systems. Perhaps most significantly, the direct proximity to space eliminated the need to design components to withstand launch stresses, allowing for lighter, more efficient designs optimized purely for their operational environment. The first major project completed in the floating shipyards, the Venus Orbital Laboratory, was inaugurated in year 109. This research station, constructed entirely from Venus-sourced materials, except for the most specialized scientific equipment, demonstrated the colony's capacity to build large-scale space infrastructure independently. More importantly, it established Venus as a spacecraft manufacturing center capable of producing vessels for interplanetary transport and specialized orbital operations. This manufacturing capability transformed Venus's economic relationship with Earth and the broader solar system. For most of its history, the colony had been a net consumer of Earth resources, receiving supplies, specialized equipment, and new colonists while returning primarily scientific knowledge and technological innovations. The Industrial Revolution reversed this balance, establishing Venus as a producer of finished goods valuable throughout human space. The Economic Declaration of Independence, issued by the colonial authority in year 111, formally acknowledged this transformation. The declaration noted that for the first time, the value of Venus exports to Earth and other settlements exceeded the value of imports, creating a positive trade balance. While the colony still required certain specialized items and regular population exchange with Earth, it had achieved true economic self-sufficiency, a milestone that many early skeptics of Venus colonization had considered impossible. This economic independence enabled the development of genuine trade networks connecting Venus with other human settlements throughout the inner solar system. The Interplanetary Commerce Commission, established in year 112 with representatives from Earth, Venus, Mars colonies, and orbital habitats, created standardized protocols for trade exchanges, dispute resolution, and resource valuation across diverse environments. Venus's location proved advantageous for certain trade routes. Its position in the inner solar system created more frequent transfer windows to Earth than those available from Mars, allowing more regular commerce. For trade with the asteroid belt, Venus's substantial gravity well could be used for gravitational assists that reduced fuel requirements for transport vessels, making it an efficient waypoint for certain routes. The Venusian merchant fleet, built in the floating shipyards specifically for interplanetary commerce, began regular operations in year 113. This spacecraft represented a new generation of transport vessel, highly automated, fuel-efficient, and designed for multiple consecutive journeys without major maintenance. Their distinctive golden heat shields, optimized for aerobraking in Venus's upper atmosphere, became a recognized symbol of Venusian commerce throughout the solar system. The products that fueled this trade network reflected Venus's unique industrial strengths and environmental conditions. High on the export list were specialized materials developed for Venus's extreme conditions that found applications in other harsh environments. Venusian acid-resistant coatings, originally developed to protect habitat exteriors, became essential for industrial facilities processing corrosive substances on Earth. Heat dissipation systems engineered for Venus surface operations were adapted for deep mining operations and high-temperature manufacturing processes. Electronics and control systems manufactured in Venus's low-contamination environments gained reputation for exceptional reliability and precision, becoming particularly valued for critical life support applications in other space habitats. The microgravity manufacturing capabilities of the floating shipyards produced optical components with purity and precision difficult to achieve elsewhere, creating a niche market for specialized scientific instruments and communication systems. Perhaps most significant among Venus exports were the biological products developed through generations of adaptation to enclosed ecological systems. Genetically modified plants optimized for hydroponic cultivation in controlled environments found ready markets in Earth's increasingly controlled agricultural systems and other space settlements. Microbial packages developed for atmospheric processing and waste recycling on Venus became valuable for environmental remediation projects on Earth and life support systems elsewhere in space. The most profitable Venusian export, however, proved to be expertise rather than physical goods. The generations of experience operating in Venus's challenging environment had created unmatched knowledge in closed system management, extreme environment engineering, and sustainable resource cycling. Venus consultants commanded premium fees for designing life support systems, habitat environments, and resource management approaches for new space ventures, and increasingly for Earth's own stressed environmental systems. Venus Research University established satellite campuses on Earth and Mars, offering specialized education in atmospheric sciences, closed system agriculture, and extreme environment engineering. Graduates of these programs were highly sought after for both space ventures and Earth-based environmental management roles, creating an educational export sector that significantly contributed to the colony's economic strength. This burgeoning industrial economy created significant changes within Venusian society. New job categories emerged, from interplanetary trade specialists to industrial process engineers to microgravity manufacturing technicians. The wage economy, which had been limited in scope during the colony's earlier phases, when resource allocation was primarily managed through central planning, expanded dramatically with increased specialization and productivity variations between sectors. The introduction of the Venus credit as an internal currency in year 107 formalized this economic evolution. While resource allocation for essentials remained partially managed through the Resource Management Council, the credit system created flexibility for non-essential goods and services, allowing for market-driven allocation based on individual preferences rather than centrally determined priorities. The growing industrial base and expanding trade networks attracted increasing interest from Earth-based corporations seeking to establish operations in Venus's unique environment. The colonial authority, mindful of maintaining Venusian autonomy while benefiting from external investment, established the Corporate Participation Framework in year 109. This framework allowed Earth corporations to establish manufacturing facilities or research operations on Venus under license, with specific requirements for local employment, technology transfer, and profit sharing with the colonial government. Several major Earth corporations established significant presence under this framework, bringing additional capital, specialized expertise, and expanded trade connections. These corporate operations integrated into the Venusian industrial ecosystem, but maintained distinct identities and management structures, sometimes creating friction with locally developed enterprises and the existing social structures of the colony. These tensions culminated in what became known as the Great Labor Dispute of years 114 through 115. The first major industrial action in Venus's history. The dispute originated in Production Platform Delta, where Universal Manufacturing Incorporated, or UMI, an Earth-based corporation, had established operations producing specialized electronics for export. UMI's management implemented productivity standards and work schedules based on Earth manufacturing models, without fully accounting for the unique conditions and established practices of Venus. When worker representatives raised concerns about these expectations, company leadership initially dismissed them as resistance to efficient practices, citing their extensive Earth experience as justification for their approaches. The situation escalated when UMI announced a new compensation structure that tied worker pay directly to production metrics derived from Earth facilities. Venus-born workers, in particular, objected to both the metrics themselves and the implied devaluation of their Venus-specific knowledge and adaptations. After attempts at negotiation failed, approximately 700 workers across multiple UMI facilities initiated a coordinated work slowdown in year 114. The dispute rapidly expanded beyond UMI as workers in other corporate facilities, and even some colonial operations joined in solidarity, raising broader concerns about economic decision-making and the colony's relationship with Earth-based interests. At its peak, nearly 20% of Venus's industrial workforce was participating in some form of organized labor action. The colonial authority found itself in a difficult position, balancing its interest in maintaining industrial productivity with its responsibility to represent the interests of Venusian citizens. After initial attempts at mediation failed, the authority established the Industrial Relations Commission in year 115, a formal body with representatives from management, workers, and the colonial government empowered to establish binding standards for working conditions, compensation structures, and dispute resolution. The Commission's deliberations lasted nearly 4 months, during which limited industrial actions continued, while essential operations were maintained through negotiated agreements. The resulting Venusian Labor Accord established principles that would shape the colony's industrial relations for decades to come: recognition of Venus-specific working conditions and knowledge as valuable factors in productivity, guaranteed representation for workers in management decisions affecting their operations, standardized grievance procedures with neutral arbitration, and profit-sharing requirements ensuring that Venusian workers benefited directly from the economic value they created. UMI initially threatened to withdraw from Venus rather than accept these terms, but the potential loss of their investment and the strategic importance of maintaining presence in Venus's growing industrial base eventually led them to accept a modified version of the accord. Other Earth corporations, observing the resolution process, proactively adapted their operations to better integrate with Venusian expectations and practices, avoiding similar disputes. The resolution of the Great Labor Dispute marked a significant maturation of Venus's industrial society. The colony had demonstrated that its economic independence extended to setting its own terms for how industry would operate within its habitats. The balance of power between Earth-based corporations and Venusian workers had shifted decisively toward the latter, establishing precedents that would influence industrial relations throughout human space as colonies and habitats elsewhere developed their own economic autonomy. By year 115, as the most intense phase of industrial development stabilized into sustainable operations, Venus had completed its transformation from dependent colony to industrial power. The manufacturing base established during this period would continue to expand and evolve, but the fundamental shift in economic identity had been accomplished. Venus no longer imported more than it exported, no longer relied on Earth subsidies for essential operations, and no longer followed Earth's lead in determining its economic structures and priorities. The golden cities floating in Venus's clouds had become not just marvels of human adaptation to an extreme environment, but centers of production, innovation, and commerce that influenced the solar system economy. The Industrial Revolution had created a truly bidirectional relationship between Venus and Earth, not one of colony and metropole, but of distinct civilizations engaged in mutually beneficial exchange while maintaining their separate identities and interests. This economic evolution would provide the resources and capabilities for the next major phase in Venus's development: consideration of weather and how to modify the planet itself to make more of it hospitable to human presence. The industrial capacity developed during these 15 years created possibilities that the original colonists could scarcely have imagined. setting the stage for debates about humanity's long-term relationship with its second planetary home. Part 10 towards terraforming. For more than a century, humans had adapted themselves to Venus rather than attempting to adapt Venus to human needs. The floating habitats, atmospheric resource harvesting, and even the surface mining operations had been designed to function within Venus's environment as it existed, working around the extreme temperatures, crushing pressures, and caustic atmosphere rather than trying to change them. But as the colony's industrial capacity expanded and its population continued to grow, an increasingly common question emerged. Could Venus itself be modified to become more hospitable to human life? This question sparked what became known as the Great Modification Debate, a 15-year discussion that would fundamentally shape humanity's relationship with its second planetary home and establish precedents for how civilization might approach other worlds in the future. The debate began in scientific circles at Venus Research University, but quickly expanded to engage the entire colony and eventually Earth as well, becoming one of the most significant philosophical and practical controversies of its era. The foundational question seemed simple: should humans attempt to terraform Venus? But this apparent simplicity masked a host of complex scientific, ethical, and practical considerations that different stakeholders approached from widely varying perspectives. The terraforming advocates, who gained prominence around year 116, argued that humanity had both the right and the responsibility to make Venus more Earth-like. They pointed to evidence that Venus may once have had conditions similar to early Earth before a runaway greenhouse effect transformed it into its current state. From this perspective, terraforming would be restoring Venus to what might have been its natural evolution had different conditions prevailed. More practically, they argued that the floating habitat model, while successful, imposed fundamental limitations on Venus's human-carrying capacity. Even with continued expansion of cloud cities, the population would eventually reach limits imposed by atmospheric resources and the challenges of maintaining artificial environments indefinitely. Terraforming offered the potential to eventually make Venus's surface habitable, multiplying the available living space by orders of magnitude. In opposition, the Natural Preservation Coalition emphasized that Venus, while hostile to human life, was a unique planetary system worthy of protection in its own right. They argued that Venus's current state represented billions of years of natural evolution, and humans had no right to fundamentally alter an entire world based on their own preferences. This position gained particular support among second- and third-generation Venusians, who had developed a complex relationship with their adopted world, seeing beauty and value in its alien characteristics rather than merely hostility to human life. Scientific considerations complicated both positions. Venus's transformation would be an undertaking measured in centuries or millennia, far beyond the lifespan of any individual or even any particular generation. The full consequences of planetary-scale intervention could not be predicted with certainty, creating the risk of unintended outcomes that might prove worse than the original conditions. Additionally, while no evidence of indigenous life had been found on Venus despite extensive exploration, the possibility of undiscovered microscopic organisms in certain environmental niches could not be definitively ruled out, raising questions about what might be destroyed through terraforming. Economic factors entered the debate as well. The Industrial Revolution had created prosperity based on Venus's current conditions and specializations. Certain industries, particularly those manufacturing materials designed for extreme environments, might actually lose value if Venus became more Earth-like. Conversely, terraforming would create unprecedented economic opportunities in planetary engineering that would likely span generations of activity. By year 118, the debate had essentially reached an impasse, with strongly held views on both sides and no clear consensus about how to proceed. This stalemate was broken by the emergence of a third perspective, the gradualist approach, that would eventually shape Venus's path forward. The gradualists, led by a coalition of scientists and policy experts from both Venus and Earth, proposed neither full terraforming nor complete preservation, but rather limited, reversible interventions that could generate scientific knowledge while improving conditions in specific ways. This approach emphasized careful experimentation, continuous monitoring, and the establishment of ethical and scientific safeguards before any irreversible changes were implemented. After 3 years of intensive debate, the colonial authority established the Planetary Modification Commission in year 121 to develop a framework for potential interventions. The commission included representatives from scientific disciplines, ethics committees, industrial sectors, and cultural preservation advocates, with both Venusian and Earth perspectives represented. Their mandate was not to decide whether modification should occur, but to establish principles for how such modifications might be approached, if approved through political processes. The Commission's work resulted in the Venus Planetary Charter, ratified in year 122. This landmark document established several key principles that would guide all future modification efforts. First, the measurable improvement standard required that any modification must have clearly defined, measurable objectives that would demonstrably improve Venus's habitability or scientific understanding, while minimizing negative impacts on existing systems. Second, the reversibility principle stipulated that initial modifications should be designed to be reversible if negative consequences emerged, with irreversible changes permitted only after extensive testing of reversible approaches. Third, the intergenerational responsibility clause acknowledged that planetary modifications would affect future generations who could not participate in current decision-making. It required establishment of trust funds, documentation systems, and multi-generational governance structures to ensure that future inhabitants would have resources to address unforeseen consequences and agency in continuing or altering modification programs. Fourth, the Scientific Transparency Protocol mandated comprehensive monitoring and public sharing of all data related to modification efforts, ensuring that the entire scientific community could evaluate outcomes and raise concerns about unexpected developments. Finally, the cultural and environmental preservation requirement established that certain regions of Venus would remain permanently unmodified as scientific control areas and cultural heritage zones, preserving Venus's original state for study and appreciation by future generations. With these principles established, the colonial authority authorized the first experimental intervention, Pilot Project Alpha, which began implementation in year 123. Rather than attempting comprehensive terraforming, Alpha focused on a limited but significant objective: reducing carbon dioxide levels in a contained atmospheric test region. The project established a 20-kilometer diameter atmospheric test zone in Venus's upper clouds, using a network of specialized drones to create a semi-permeable boundary that allowed limited gas exchange with the surrounding atmosphere while maintaining the integrity of the test area. Within this zone, engineers deployed the first generation of large-scale atmospheric processors, massive machines that extracted carbon dioxide from the air and converted it to solid carbon and oxygen through an energy-intensive catalytic process. These processors represented a dramatic scaling up of the carbon extraction technology that had been used for life support throughout the colony's history, where habitat systems had processed just enough carbon dioxide to provide oxygen for residents. These new machines were designed to process atmospheric volumes thousands of times larger. Powered by dedicated solar arrays that captured Venus's abundant sunlight, they operated continuously, gradually changing the atmospheric composition within the test zone. The project faced significant technical challenges. The processors required constant maintenance due to the corrosive environment, necessitating the development of highly automated repair systems and specialized maintenance drones. The carbon extraction process generated substantial waste heat that had to be carefully managed to prevent disruption of the atmospheric boundary. Most challenging was maintaining the test zone's integrity against Venus's powerful winds, requiring continuous adjustment of the drone network that defined its boundaries. Despite these difficulties, Pilot Project Alpha achieved its initial objectives by year 125. Within the test zone, carbon dioxide levels had been reduced by approximately 15%, with corresponding increases in oxygen. While this change was far from creating breathable air, it represented the first controlled, intentional modification of Venus's atmosphere by human action, a proof of concept that larger-scale interventions were technically feasible. Equally important, the project generated invaluable data about atmospheric dynamics and chemical interactions that improved models of how Venus's global systems might respond to more extensive modifications. The precision of these models was crucial for predicting potential unintended consequences before they occurred, addressing one of the primary concerns raised by modification skeptics. The success of Alpha led to approval of more ambitious projects addressing different aspects of Venus's inhospitable conditions. Among the most significant was the Sunshield feasibility study initiated in year 126. This project examined the potential for deploying massive orbital structures at Venus's L1 Lagrange point, a location where the gravitational influences of Venus and the Sun balance each other, allowing objects to maintain a stable position relative to both bodies. These proposed sunshields would block a portion of incoming solar radiation, gradually cooling Venus by reducing the energy input that maintained its extreme temperatures. The concept had existed theoretically for decades, but the industrial capabilities developed during Venus's Industrial Revolution now made physical implementation conceivable for the first time. The study evaluated multiple shield designs, from solid reflective surfaces to gossamer-thin mesh structures that would filter specific wavelengths while allowing others to pass. Each approach offered different trade-offs in terms of material requirements, construction complexity, and cooling efficiency. The most promising concept emerged as a Venetian blind design, a series of adjustable reflective slats that could modulate the amount of sunlight reaching Venus, providing precise control over the cooling process. Construction of these enormous structures would require unprecedented manufacturing capacity, even with the capabilities of the floating shipyards. The study concluded that a phased approach would be necessary, beginning with a demonstration shield covering approximately 0.1% of Venus's sunward-facing area and gradually expanding coverage as manufacturing capabilities increased and effects were carefully monitored. While the Sunshield project remained in the study phase during this period, practical implementation began on another key aspect of potential terraforming: large-scale carbon capture and sequestration. Building on the success of Pilot Project Alpha, the Colonial Authority approved deployment of atmospheric processors beyond the test zone, distributed strategically through Venus's upper atmosphere. The Carbon Reduction Network, initiated in year 128, consisted of 100 autonomous processing platforms, each housing multiple carbon extraction units and the energy systems to power them. Unlike the test zone processors, these platforms operated directly in Venus's unmodified atmosphere, extracting carbon dioxide and converting it to solid form. The solid carbon was compressed into dense blocks for either industrial use or permanent sequestration, while the oxygen was initially released back into the atmosphere. This approach addressed one of Venus's most fundamental habitability challenges: its overwhelming carbon dioxide atmosphere, which created both the crushing surface pressure and the runaway greenhouse effect that maintained extreme temperatures. By gradually reducing atmospheric carbon dioxide, the network would theoretically reduce both pressure and temperature over extended timeframes, potentially making the surface more accessible for future human activities. The network faced scaling challenges beyond those encountered in the test zone. Maintaining and refueling 100 platforms distributed throughout Venus's turbulent atmosphere required sophisticated logistics and autonomous repair capabilities. The platforms themselves needed robust defenses against the intense storms that periodically swept through Venus's cloud layers, drawing on lessons learned during the storm era decades earlier. Most significantly, the energy requirements for large-scale carbon processing exceeded what could be practically generated through conventional solar arrays attached to each platform. This challenge led to development of the high-altitude solar grid, a network of specialized energy collection platforms positioned above Venus's cloud layer, where solar intensity was maximum. These platforms beamed power to the processing units using microwave transmission, providing the vast energy inputs required for continuous operation. By year 130, the Carbon Reduction Network had processed approximately 0.001% of Venus's total atmospheric carbon dioxide, a tiny fraction of what would be required for significant planetary change, but an important demonstration that the approach could be implemented at scale. More importantly, the network established the infrastructure and operational protocols that could be expanded over time as capabilities increased and effects were verified. The most scientifically significant outcome of these early modification efforts came not from the direct results of carbon reduction or Sunshield studies, but from the unprecedented monitoring systems deployed to track their effects. The Venus Environmental Monitoring Network, established in year 127, created the most comprehensive planetary observation system ever deployed, with thousands of sensors throughout Venus's atmosphere and orbit recording everything from temperature and pressure to chemical composition and energy fluxes. This monitoring network detected the first measurable planetary-scale changes resulting from human intervention by year 130. While the direct atmospheric modifications remained localized, the sensors identified subtle but significant shifts in atmospheric circulation patterns near the carbon reduction platforms. These changes, while minor, demonstrated that even limited human activities were capable of influencing Venus's global systems, a sobering validation of both the potential and the responsibility of planetary modification. The monitoring data also revealed that Venus's atmosphere responded to intervention in ways not fully predicted by existing models, with feedback mechanisms sometimes amplifying and sometimes dampening the intended effects. These discoveries led to major revisions in simulation models and a greater emphasis on careful, incremental approaches that could be adjusted as real-world data accumulated. As these physical projects progressed, the philosophical and ethical dimensions of planetary modification continued to evolve. The Venus Planetary Ethics Council, established in year 129, developed frameworks for evaluating not just the scientific and technical aspects of terraforming, but its moral implications as well. The Council's most significant contribution was the planetary rights doctrine, a philosophical framework that attempted to balance respect for Venus as an existing natural system with recognition of humanity's legitimate interests in creating additional habitable environments. This doctrine explicitly rejected the concept of planets as mere resources to be exploited, while also acknowledging that thoughtful modification could potentially enhance, rather than diminish, a planet's overall value and diversity. A key insight of the doctrine was the distinction between modification and standardization. Whereas early terraforming concepts had often implicitly assumed that making Venus as Earth-like as possible was the goal, the doctrine argued for approaches that would improve habitability while preserving Venus's unique characteristics. This adaptive terraforming philosophy suggested that the ideal outcome would be a Venus that humans could inhabit more extensively, but that would retain distinct Venusian qualities rather than becoming an Earth replica. This philosophical evolution reflected the growing maturity of the Venus-born population and their complex relationship with their home world. Unlike the original colonists who had necessarily viewed Venus primarily as a hostile environment to be endured, successive generations of Venusians had developed cultural and aesthetic appreciation for their world's unique qualities. They increasingly saw themselves not as displaced Earthlings, but as genuine Venusians with their own planetary identity. This perspective influenced the specific modification approaches pursued, with greater emphasis on changes that would expand human access while preserving Venus's distinctive characteristics. For instance, rather than attempting to eliminate Venus's cloud layers entirely, which some early terraforming concepts had proposed, the focus shifted to modifying their composition to reduce corrosivity while maintaining their visual and atmospheric influence. By year 130, the combined effect of these various initiatives had transformed the Great Modification debate from a binary question of whether to terraform Venus into a nuanced, multi-generational project of thoughtful planetary stewardship. The absolutist positions that had dominated early discussions gave way to a pragmatic consensus around careful, incremental modification guided by scientific evidence, ethical principles, and respect for both humanity's needs and Venus's intrinsic value. While the physical changes to Venus remained modest at this stage, imperceptible to casual observation though measurable with sensitive instruments, the conceptual framework established during this period would guide humanity's relationship with Venus for centuries to come. The principles developed through the Venus Planetary Charter and subsequent ethical frameworks would later influence humanity's approach to other worlds as well, establishing precedents for responsible intervention that balanced human interests with respect for existing planetary systems. As this phase of Venus's development concluded, the colony had demonstrated not just the technical capability to begin modifying its adopted world, but the wisdom to approach this unprecedented power with appropriate caution and foresight. The path toward terraforming had been opened, but it would be traveled with careful steps, continuous reassessment, and a deep appreciation for the responsibility that came with reshaping a world that had existed for billions of years before human arrival. The floating habitats remained humanity's primary home on Venus, continuing to evolve and expand with the growing population. But for the first time, the boundary between the habitable cloud cities and the inhospitable planet beyond them had become permeable, not through dramatic transformation, but through the first tentative steps toward a future where humans might live with Venus rather than merely above it. Part 11. Political Evolution. By year 130, the Venus colony had achieved remarkable milestones in industrial development, scientific advancement, and the beginnings of planetary modification. Yet one dimension of colonial development remained incomplete: the political relationship between Venus and Earth. While the Venus Accord and subsequent arrangements had granted substantial autonomy to the colonial authority, formal ties of oversight and dependency remained, creating a political structure that an increasing number of Venusians found inadequate for their maturing society. The years between 130 and 145 would see a fundamental restructuring of these relationships, completing Venus's evolution from outpost to independent political entity. The seeds of this political transformation had been present throughout the colony's history. The social contract crisis of years 54 and 55 had established greater local authority while maintaining Earth oversight. The Venus Accord had formalized colonial self-governance in internal matters, while preserving Earth's ultimate authority in specific domains, including interplanetary relations, military matters, and certain aspects of resource allocation. This arrangement had served adequately during the colony's development phases, but as Venus's population grew and its industrial and scientific capabilities expanded, the limitations of this framework became increasingly apparent. In year 132, the autonomy movement emerged as a formal political organization, bringing together various independence-minded factions under a unified platform. Unlike earlier independence advocates who had sometimes taken confrontational approaches, the autonomy movement emphasized Venus's readiness for self-governance rather than grievances against Earth authority. Their foundational document, A Mature Relationship, argued that complete political independence would benefit both Venus and Earth by allowing each to pursue its distinct interests while maintaining mutually beneficial connections. The movement gained rapid support across demographic groups, but particular strength among the Venus-born population, now in its fourth generation. These Venusians, having never personally experienced Earth, viewed the continuing political subordination to a distant planet as an anachronism, a vestige of the colony's founding conditions that no longer reflected current realities. For them, Venus was not a colony of Earth, but simply home, and its government should derive authority solely from its own citizens. The economic strength developed during the Industrial Revolution provided practical leverage for these political aspirations. Venus now supplied critical materials and technologies to Earth and other settlements, creating interdependencies that shifted the balance of power in interplanetary relations. The Venus Council of Trade and Industry, representing the colony's major production sectors, issued economic impact analyses demonstrating that disruption of Venusian exports would significantly affect Earth's advanced manufacturing and habitat construction industries. Earth's response to the growing independence movement was not uniform. Some Earth nations that had heavily invested in Venus's development opposed significant changes to the existing relationship, concerned about protecting their investments and access to Venus-produced resources. Others recognized the inevitability of political evolution and preferred to negotiate favorable terms rather than resist the broader trend. Earth's own political complexities, with competing national interests and varying degrees of commitment to space development, created a fragmented response that the autonomy movement skillfully navigated. The catalyst for formal negotiations came in year 135 with the Representation Declaration, in which the colonial authority formally requested recognition of Venus as a sovereign political entity with the right to represent itself in interplanetary affairs. The declaration carefully balanced assertiveness with reassurance, emphasizing continued partnership with Earth while insisting on political equality rather than subordination. This approach proved effective in bringing Earth authorities to the negotiating table. Rather than rejecting the declaration outright, Earth's major spacefaring nations proposed formal talks to establish a new framework for Earth-Venus relations. These negotiations began in year 136, alternating between locations on Earth and Venus to symbolize the equal standing of both parties. The negotiations were complex, addressing everything from resource rights to citizenship status to defense responsibilities. A particularly challenging issue was the status of Venus-born citizens, whether they would retain Earth citizenship rights while gaining Venusian citizenship, or whether a clear distinction would be established. Similarly complex was determining ownership and control of orbital facilities that had been constructed with mixed Earth and Venus investment and labor. After nearly 18 months of intensive diplomacy, the Treaty of New Sky was signed in year 138. Named after the conference facility in Cloud Haven Metropolis, where the final sessions took place, the treaty represented a comprehensive restructuring of Venus's political status and its relationship to Earth and the broader human presence in space. The treaty's core provisions established Venus as a fully self-governing entity with complete sovereignty over its atmospheric habitats, surface operations, and orbital facilities. The colonial authority was replaced by the Venus planetary government, with its leadership determined solely by Venusian citizens without requirement for Earth approval. This government received full authority to establish its own laws, manage its resources, conduct independent trade, and represent Venus in relations with other political entities throughout the solar system. Alongside this independence, the treaty established the Solar System Alliance, a new interplanetary framework that included Earth, Venus, the major Mars settlements, and representatives from lunar and orbital habitats. This alliance created mechanisms for cooperation on matters of common interest, including scientific research, disaster response, and the development of space resources beyond established settlements. Unlike previous arrangements where Earth held predominant authority, the alliance operated on principles of sovereign equality, with each member having equal standing regardless of population or development level. For individual citizens, the treaty established dual citizenship as the default status, with both Venus-born and Earth-born residents of Venus holding rights as citizens of both worlds. This approach recognized the continuing familial and cultural connections between the planets, while establishing the primary allegiance of Venus residents to their immediate community. The treaty guaranteed freedom of movement between Earth and Venus for dual citizens, subject only to practical limitations of transport availability and habitat capacity. Resource rights received particular attention, with the treaty establishing Venus's exclusive control over its atmospheric and surface resources, while requiring compliance with scientific and ethical standards for planetary modification established in the Venus Planetary Charter. Earth entities retained certain limited resource access rights based on historical investment, but these were defined as commercial arrangements rather than political privileges, subject to Venusian regulation and taxation. The Treaty of New Sky represented a peaceful transfer of sovereignty unprecedented in human history. Unlike Earth's colonial independence movements, which had often involved conflict and revolution, Venus achieved political autonomy through negotiation and mutual recognition of changing circumstances. This outcome reflected both the practical realities of space settlement, where interdependence remained essential for survival, and the evolution of political thinking that had occurred since Earth's colonial era. With independence formally established, Venus faced the challenge of developing governance structures appropriate to its unique environment and social organization. The transitional government established by the treaty commissioned a planet-wide constitutional process to determine the permanent form of Venusian governance. This process, lasting nearly 2 years, involved extensive public consultation through digital forums, habitat assemblies, and specialized working groups addressing different aspects of governance. The distributed nature of Venus's population, spread across multiple floating habitats and orbital facilities, required creative approaches to representation and decision-making that differed substantially from Earth models based on geographic districting. The resulting constitution of the Venusian cloud domains, ratified in year 140, established a distinctive governance structure specifically adapted to Venus's environmental and social realities. Rather than organizing representation geographically, the Constitution created a dual system based on both physical habitats and functional domains of activity. Each major habitat elected its own council responsible for local operations, safety regulations, and resource allocation within the habitat. Simultaneously, cross-habitat representative bodies were established for major activity domains including scientific research, industrial production, environmental management, education, and cultural development. These domain assemblies addressed issues specific to their areas of focus, developing specialized expertise while ensuring that policies reflected the perspectives of practitioners throughout the Venus system. Coordinating these various bodies was the Venusian High Council, a 23-member executive body with representatives from both habitat councils and domain assemblies. The High Council held responsibility for colony-wide policies, interplanetary relations, and resolving conflicts between habitat and domain authorities. Council members served staggered 6-year terms, ensuring continuity while allowing for regular democratic renewal. This governance system acknowledged the reality that Venusian citizens identified both with their specific habitat communities and with their professional or activity domains that often spanned multiple habitats. A scientist might feel equal allegiance to her home in Cloud Haven 5 and to the scientific community distributed throughout Venus, with both identities deserving political representation. The overlapping authority of habitat and domain governance ensured that both dimensions of identity received appropriate consideration in policy development. Judicial functions were handled by the Venusian Court of Review, which adjudicated constitutional questions, resolved disputes between governance bodies, and served as the final appeal for individual rights cases. The court's 9 justices were appointed by the High Council from nominees provided by the legal community, serving single 12-year terms to insulate them from political pressure while ensuring eventual turnover. This governance structure proved remarkably effective at addressing the specific challenges of Venus's environment. The Habitat Councils managed the immediate safety and resource needs essential for survival in the floating cities, while the domain assemblies developed specialized expertise in their areas of focus. The High Council provided strategic direction and spoke with a unified voice in interplanetary relations, while the Court of Review ensured adherence to constitutional principles. The Constitution also incorporated the Common Resources Doctrine, a legal framework specifically addressing the shared nature of Venus's atmosphere. Unlike land on Earth or Mars, Venus's atmospheric environment could not be meaningfully divided into exclusive territories. The atmospheric currents that carried the floating habitats, the cloud layers that protected them from solar radiation, and the chemical cycles that influenced habitat environments were all inherently shared resources affecting all colonists simultaneously. The doctrine established the principle that Venus's atmosphere was the common heritage of all its inhabitants, to be managed collectively for the benefit of current and future generations. Private or habitat-specific activities that affected the broader atmosphere required approval through common resource governance mechanisms, with decisions based on scientific assessment of impacts and fair distribution of benefits and risks. This approach proved particularly important as planetary modification efforts expanded. The Carbon Reduction Network and other terraforming initiatives had potential long-term effects on all habitats regardless of their direct participation. The Common Resources Doctrine ensured that these projects received appropriate oversight and that their benefits would be shared throughout Venusian society rather than accruing primarily to the implementing organizations. Implementation of the doctrine led to establishment of the Atmospheric Commons Trust in year 142, a specialized governance body with representation from all habitats and relevant domain assemblies. The trust received authority to regulate activities affecting atmospheric composition, circulation patterns, and energy balance, along with responsibility for monitoring planetary-scale changes and ensuring compliance with the ethical frameworks established in the Venus Planetary Charter. The Trust's work balanced current use rights with preservation for future generations, scientific research needs with industrial access, and habitat-specific interests with colony-wide considerations. Its decisions were binding on both public and private entities throughout Venus, creating a coherent management framework for the shared atmospheric environment that all Venusians ultimately depended upon. With its internal governance established, independent Venus turned its attention to developing direct diplomatic relationships with other human settlements throughout the solar system. The Venus Diplomatic Corps, formally established in year 141, represented a significant evolution from the previous arrangement, where Earth had conducted interplanetary diplomacy on Venus's behalf. The Corps established permanent missions on Earth, Mars, Luna, and major orbital habitats, staffed primarily by Venus-born diplomats specially trained in interplanetary relations. These representatives negotiated directly with their counterparts on matters including resource access, scientific cooperation, technology exchange, and migration protocols. While operating within the broader framework of the Solar System Alliance, they pursued Venus-specific interests that sometimes diverged from Earth's priorities. Relations with the Mars colonies proved particularly significant. Despite their environmental differences, Venus and Mars shared the experience of adapting human society to non-Earth conditions and developing political structures independent from Earth oversight. The Venus-Mars Cooperative Framework, established in year 143, created special arrangements for technology exchange, scientific collaboration, and preferred trade terms between the two planetary settlements. This relationship occasionally created tensions with Earth, as the independent planets sometimes aligned their positions on resource access rights and regulatory standards in ways that challenged Earth's historical dominance of space development. The emergence of what some called a planets bloc within the Solar System Alliance represented a significant evolution in solar system politics, the beginning of a multipolar system rather than one centered exclusively on Earth. Venus also developed specialized relationships with the asteroid mining operations emerging in the belt between Mars and Jupiter. Venus's location provided logistical advantages for certain asteroid trade routes, while its manufacturing capabilities offered processing services for raw materials extracted from these small bodies. The Belt Commerce Treaty of year 144 established Venus as a major waypoint in emerging resource flows from the outer system to the inner planets. Throughout this political evolution, Venus's relationship with Earth remained complex and multifaceted. The Treaty of New Sky had established formal independence, but the planets remained deeply connected through historical ties, continuing migration, trade relationships, and cultural exchange. Earth remained the largest market for Venusian exports and the primary source of certain specialized goods and technologies that Venus had not yet developed capacity to produce locally. Family connections transcended political boundaries, with many Venusians maintaining close relationships with relatives on Earth. Educational exchanges flourished, with Venus Research University hosting Earth students seeking expertise in Venus's specialized fields, while Venusian students traveled to Earth for studies in disciplines still more advanced there. Cultural productions from both worlds found audiences on the other, with Venusian artistic forms like atmospheric harmonics gaining followings on Earth, while Earth's historical cultural heritage remained influential on Venus. These connections created a relationship more nuanced than either simple independence or continued dependence. Venus had achieved political sovereignty and direct control of its affairs, but existed within an interconnected system where complete isolation would have been neither practical nor desirable. The planets functioned as distinct political entities while maintaining the familial relationship inherent in their shared human heritage. Tensions did emerge in specific areas where interests diverged. Earth corporations sometimes resisted Venusian regulatory requirements that differed from familiar Earth standards, particularly in resource extraction operations. Migration policies occasionally created friction, with Venus carefully managing population growth to match habitat capacity, while some Earth nations pressed for greater access for their citizens. Scientific priorities sometimes differed, with Venus emphasizing research directly relevant to its environment, while Earth sought broader knowledge exploration. The relationship was further complicated by Venus's continuing technological advancement in areas previously dominated by Earth expertise. By year 145, Venus had achieved superiority in several specialized fields, including atmospheric engineering, extreme environment materials, and closed system ecology. Earth entities increasingly licensed Venusian technologies rather than the reverse, creating adjustment challenges for Earth industries accustomed to technological dominance. Perhaps most significantly, Venus's approach to planetary modification established precedents that potentially constrained Earth's options for development of other celestial bodies. The ethical frameworks and scientific protocols established in the Venus Planetary Charter became de facto standards within the Solar System Alliance, requiring similar careful approaches to potential terraforming or resource extraction on other worlds. Some Earth interests that had envisioned more aggressive exploitation of space resources viewed these constraints as unduly restrictive, creating occasional diplomatic friction. Despite these tensions, the relationship remained fundamentally cooperative, with both planets recognizing their interdependence and shared interest in human flourishing throughout the solar system. The regular Summit of the Worlds, established in year 145, brought together leadership from Earth, Venus, Mars, and other major settlements to address system-wide challenges including scientific coordination, disaster response preparation, and the legal frameworks for development of currently uninhabited bodies. By the end of this 15-year period, Venus had completed its political evolution from colony to sovereign entity. Its distinctive governance structures, tailored to its unique environment, had proven effective at managing both internal affairs and external relations. The Venusian identity, once merely a descriptor for location, had matured into a genuine political and cultural designation, embraced by the planet's residents and recognized throughout human civilization. This political maturation complemented the scientific, industrial, and social development of previous eras, creating a truly independent branch of human civilization among Venus's clouds. While continuing to draw upon its Earth heritage and maintain connections with its ancestral world, Venus had definitively established its own path forward, not as an extension of Earth society, but as a parallel human civilization adapted to and shaped by its distinctive planetary environment. As Venus approached the 150th anniversary of human arrival, it stood as a remarkable testament to human adaptability, ingenuity, and social evolution. From the precarious early habitats to a thriving, independent cloud civilization with its own governance, culture, and relationship to its planetary home, the journey had transformed not just Venus, but humanity's understanding of its own potential to create home in even the most unlikely environments the solar system offered. Part 12, Looking to the Stars. As the Venus colony approached its sesquicentennial, the 150th anniversary of humanity's first permanent presence in the clouds of Earth's sister planet, the floating habitats had evolved from precarious outposts to a thriving civilization. What had begun as a daring scientific endeavor had matured into a sovereign society with its own governance, culture, industry, and aspirations. The final 5 years before this historic milestone became a period of both reflection on the remarkable journey already completed and bold planning for the centuries to come. Preparations for the sesquicentennial commemoration began in year 145, with the establishment of the Legacy Commission charged with documenting and celebrating the colony's history. This body brought together historians, artists, scientists, and representatives from Venus's oldest families to create what would become the most comprehensive account of the colony's development ever assembled. Drawing on archives, personal records, scientific data, and oral histories passed through generations, the Commission produced not merely a factual chronicle, but a deeply human story of adaptation, perseverance, and transformation. The centerpiece of this historical work was the Founders' Archive, a publicly accessible repository containing detailed records of the colony's establishment and early years. Many of these materials had been preserved but not widely available, including personal journals of first-wave colonists, original engineering specifications for Cloud Haven 1, and unedited video recordings of key moments like the deployment of the first habitat and the acid storm crisis. Making these primary sources broadly accessible created a direct connection between contemporary Venusians and their predecessors, strengthening the sense of continuity across generations. Particularly moving were the recovered audio recordings of conversations among the original habitat design team as they worked through the seemingly insurmountable challenges of creating a permanent human presence in Venus's clouds. The mixture of technical problem-solving, personal doubts, and unwavering determination captured in these informal exchanges humanized figures who had sometimes been elevated to almost mythical status in colonial history. Contemporary Venusians could hear the actual voices of their civilization's founders, complete with the hesitations, humor, and humanity that formal histories sometimes overlooked. As the sesquicentennial approached, the commemoration expanded beyond historical documentation to include the Venus 150 exhibition, a planet-wide series of events, displays, and ceremonies celebrating the colony's achievements and distinctive culture. Each habitat contributed unique elements reflecting its specializations and community character, creating a distributed festival that engaged the entire Venusian population. The Grand Concourse in Cloud Haven Metropolis hosted the technological exhibition, showcasing the evolution of habitat design, life support systems, and Venus-specific technologies from the primitive equipment of Year 1 to the sophisticated systems of Year 150. Physical artifacts including sections of the original Venuskin coating, early atmospheric processing units, and even a preserved maintenance drone from the storm era allowed visitors to trace the technological journey that had made their world possible. Cloud Haven 7, the newest major habitat, hosted the cultural pavilion featuring Venusian artistic traditions that had emerged over generations. From the atmospheric harmonics compositions that used Venus's winds as musical inspiration to the distinctive architectural aesthetics of the floating habitats, the exhibition demonstrated how thoroughly humans had not merely survived, but created genuine culture adapted to their unusual environment. Particularly striking was the evolution of Venusian visual arts, which had developed unique approaches to color and perspective influenced by the constant golden light filtered through Venus's clouds. The most ambitious element of the commemoration was the Voices of Venus project, which recorded personal stories from citizens representing every era, habitat, and sector of Venusian society. These narratives, collected in both video and text formats, created a multifaceted portrait of life among the clouds, the everyday experiences, challenges, and joys that collectively defined Venusian identity. The project particularly emphasized perspectives from Venus-born citizens across multiple generations, documenting the emergence of a genuinely Venusian worldview distinct from Earth-originated perspectives. On the sesquicentennial day itself, marking exactly 150 years since the deployment of Cloud Haven 1, a synchronized ceremony took place across all habitats, orbital facilities, and Earth locations with significant Venusian populations. The highlight was a planet-wide moment of silence followed by the atmospheric symphony, a musical composition created specifically for the occasion that was performed simultaneously in every habitat, with local musicians coordinated through the colony's communication network to create a single unified performance spanning the entire human presence on Venus. Beyond commemoration, the sesquicentennial period also featured significant advances that would shape Venus's future development. Perhaps most important was the unveiling of the third-generation habitat design that would define the next century of expansion. While previous habitat generations had essentially refined the same basic approach, floating platforms using breathable air for buoyancy, the third-generation design represented a fundamental re-examination of how humans could create permanent homes in Venus's atmosphere. The prototype for this revolutionary approach, designated Nova Horizon, began construction in year 147 based on decades of research at Venus Research University's Advanced Habitat Design Institute. Rather than the relatively compact, self-contained structures of earlier habitats, Nova Horizon utilized a distributed architecture spread across a much larger atmospheric volume. Its core comprised multiple interconnected platforms sharing structural support and life support systems, but with greater distance between elements to reduce vulnerability to localized atmospheric disturbances. The most striking innovation was Nova Horizon's dynamic configuration capability. Unlike earlier habitats that maintained relatively fixed internal arrangements, the third-generation design incorporated extensive modularity that allowed reconfiguration as needs evolved. Entire sections could be detached, moved, and reattached without compromising habitat integrity, creating unprecedented flexibility for expansion and adaptation. This approach drew inspiration from biological systems that grow and remodel themselves in response to changing conditions rather than following fixed architectural plans. Nova Horizon's life support systems represented similarly fundamental rethinking of human sustainability in Venus's atmosphere. Where previous generations had relied primarily on mechanical and chemical processes for atmospheric management, the third-generation design incorporated extensive biological systems engineered specifically for Venusian conditions. Vast living walls of genetically modified algae and bacteria processed carbon dioxide more efficiently than mechanical systems, while specialized fungal networks broke down and recycled waste materials with minimal energy input. These biological systems created habitats that were partially alive in a meaningful sense, not merely mechanical structures, but integrated ecosystems where engineered organisms worked alongside mechanical systems to maintain conditions for human habitation. This approach dramatically improved resilience, as biological systems could self-repair and adapt to changing conditions in ways mechanical systems could not. It also created interior environments that felt more natural and Earth-like despite existing within the alien context of Venus's atmosphere. The scale of potential expansion enabled by this third-generation approach was unprecedented. While the largest previous habitats accommodated populations measured in the thousands, full implementation of the Nova Horizon concept could theoretically support millions distributed across interconnected habitat networks. This capacity could finally move Venus beyond the population constraints that had limited its development despite 150 years of continuous expansion. Initial sections of Nova Horizon became operational in year 149, with the first residents transferring from older habitats to evaluate the design in practice. Their experiences confirmed the theoretical advantages while identifying refinements that would be incorporated into full-scale implementation planned for the colony's second century. The success of this prototype established the framework for Venus's next major expansion phase, potentially transforming the colony from a significant but limited human settlement to a genuine civilization comparable to Earth in complexity, if not in absolute population. Parallel to these advances in atmospheric habitation, the sesquicentennial period saw breakthrough developments in surface access technology that promised to fundamentally change humanity's relationship with Venus's hostile surface. The Deep Surface Initiative, launched in year 146, integrated decades of incremental advances in high-temperature materials, cooling systems, and pressure management into comprehensive solutions for extended human operations on the surface. The centerpiece of this initiative was the Vulcan Surface Vehicle, a mobile habitat capable of sustaining a small human crew on Venus's surface for up to 30 days continuously. Unlike previous surface facilities that had required constant energy input to maintain habitable conditions, the Vulcan utilized advanced thermal management systems that created a sustainable equilibrium between the extreme external environment and the protected interior. Key to this capability was the layered cooling approach that combined multiple technologies working in concert. The external shell incorporated phase change materials that absorbed heat through controlled melting processes, while an intermediate layer used closed-loop fluid systems to transport heat away from the crew compartment. The innermost layer featured active cooling systems using high-efficiency heat pumps powered by thermal generators that actually utilized Venus's extreme heat as an energy source, essentially turning the planet's hostility into a resource. This thermal management system allowed the Vulcan to operate without constant resupply from the floating habitats above, creating the possibility of genuine exploration rather than merely brief visits to predetermined sites. The vehicle's mobility systems used specialized high-temperature mechanical components with minimal electronics exposed to the external environment, allowing traversal of Venus's varied terrain at modest but adequate speeds. The first Vulcan mission deployed in year 148, landing in the Avda Regio highlands, where conditions were marginally less extreme than Venus's average. Over 18 days, the 6-person crew conducted extensive geological surveys, materials testing, and environmental monitoring, traveling more than 100 kilometers across previously unexplored terrain. Their findings dramatically expanded understanding of Venus's surface processes and resource distribution, identifying mineral concentrations that would later become targets for expanded extraction operations. Beyond its scientific achievements, the Vulcan mission represented a psychological milestone for the Venus colony. The surface was no longer merely a hostile environment to be studied remotely or briefly visited under extreme duress, but a frontier that humans could meaningfully explore and potentially utilize. While Venus would remain primarily a cloud civilization for the foreseeable future, the expanded surface access created new possibilities for resource utilization, scientific research, and eventual surface facilities that could complement the floating habitats above. The technological advances enabling extended surface operations also contributed to accelerated planetary modification efforts during this period. The carbon reduction network expanded significantly, with next-generation atmospheric processors deploying technologies originally developed for the Vulcan's environmental systems. These enhanced processors improved carbon extraction efficiency by approximately 30%, accelerating the gradual reduction of Venus's dense carbon dioxide atmosphere. While these modifications remained modest at planetary scale, total atmospheric carbon dioxide had decreased by less than 0.1% after decades of operation. The improved technologies established the foundation for longer-term transformation. Models projected that with continued expansion of the processor network and implementation of the orbital sunshields that had moved from study to early prototype construction, measurable cooling of Venus's surface could be achieved within the next century. These projections fueled debates about how extensively Venus should be modified, debates that reflected the colony's evolving philosophical understanding of its relationship with its planetary home. This philosophical evolution represented perhaps the most significant development of the sesquicentennial period. As the colony reached the 150th anniversary of human arrival, Venusian thinkers articulated what came to be known as the multi-planet perspective, a distinctive worldview emerging from generations of life beyond Earth. This perspective moved beyond early space advocacy that had viewed other worlds primarily as resources or escape hatches for Earth, toward a more nuanced understanding of humanity as a genuinely multiplanetary species with diverse branches adapted to different environments. The Multi-Planet Manifesto, published by the Venus Philosophical Society in year 149, articulated key principles of this emerging perspective. It argued that humanity's future lay not in simply replicating Earth conditions throughout the solar system, but in developing diverse adaptations to different planetary environments, each creating unique branches of human civilization that would collectively enrich the species. The manifesto explicitly rejected the notion that Earth conditions represented the only valid template for human habitation, instead celebrating the distinctive cultures and approaches that had emerged in each settled environment. For Venusians, this perspective provided philosophical grounding for their increasingly distinct identity. Their floating world among the clouds was not merely a compromise necessitated by Venus's hostile surface, but a unique expression of human adaptability that had created its own aesthetic, social structures, and relationship with its environment. The manifesto argued that cloud cities should be recognized as a legitimate and valuable form of human settlement in their own right, not merely as precursors to potential surface habitation following terraforming. This philosophical framework influenced practical approaches to Venus's continuing development. Rather than focusing exclusively on making Venus more Earth-like through terraforming, the colony increasingly pursued what philosophers termed adaptive harmonization, selective modifications that made Venus more amenable to expanded human presence while preserving its distinctive characteristics. This approach sought a middle path between complete planetary transformation and absolute preservation, recognizing both human needs and the value of Venus's unique planetary identity. The multi-planet perspective extended beyond philosophical discourse to shape Venus's practical relationships with other human settlements throughout the solar system. As the sesquicentennial approached, Venus established formal cooperative frameworks with the emerging settlements in the outer solar system. particularly the Jovian moon colonies and the first habitats in Saturn's orbit. These relationships emphasized knowledge transfer rather than direct resource exchange, with Venus sharing its hard-won expertise in closed-system habitation, extreme environment adaptation, and sustainable governance. The Outer Worlds Initiative, established in year 147, created formal exchange programs bringing personnel from these developing settlements to Venus for training in habitat management, life support technologies, and social systems adapted for isolated communities. Simultaneously, Venusian specialists traveled to these distant outposts to provide direct assistance with implementation challenges. These exchanges created human connections that transcended the vast distances involved, establishing Venus as a key node in humanity's expanding network of settlements rather than merely one branch of a strictly Earth-centered system. This role as a stepping stone for further expansion reflected Venus's transition from frontier to established civilization. After 150 years of development, the cloud colony had accumulated knowledge, technologies, and social structures that newer settlements could adapt for their own environments, rather than reinventing through trial and error. The Venus model of incremental adaptation, ethical habitat development, and sustainable resource management became a template that influenced human approaches to all subsequent settlement efforts, creating a legacy that extended far beyond Venus itself. As the sesquicentennial celebrations concluded, the Venusian government formally announced the bicentennial vision, a comprehensive plan guiding the colony's development toward its 200th anniversary 50 years in the future. This vision integrated aspirations across multiple domains, from habitat expansion to planetary modification to cultural evolution, creating a roadmap for Venus's continued growth as a branch of human civilization. The habitat component envisioned expansion to a population of approximately 5 million by year 200, primarily through construction of multiple third-generation habitats based on the Nova Horizon prototype. These habitats would form interconnected networks rather than isolated structures, creating metropolitan regions linking specialized environments optimized for different functions. The plan explicitly incorporated both atmospheric habitats and expanded surface facilities enabled by Vulcan-derived technologies, creating a multi-level civilization spanning Venus's most accessible environments. The planetary modification component established measured goals for atmospheric transformation, targeting 5% reduction in carbon dioxide levels and corresponding decreases in surface temperature and pressure by year 200. These modifications would expand the vertical range of comfortable human habitation within Venus's atmosphere, while making surface operations progressively less challenging, but without fundamentally altering Venus's distinctive character as a cloud-shrouded world. The plan explicitly rejected proposals for complete terraforming, instead embracing the cloud-based civilization model that had defined Venus's first 150 years while gradually expanding its scope and reach. The vision's social and cultural components emphasized continued evolution of Venusian identity while maintaining connection with broader human civilization. Educational initiatives would preserve knowledge of Earth heritage while developing distinctly Venusian approaches to art, governance, and environmental relationship. Scientific research would focus on understanding Venus as an integrated planetary system rather than merely a habitat location, with expanded exploration of previously inaccessible regions, creating a more complete picture of Venus's past, present, and potential futures. Perhaps most ambitious was the vision's cosmic component, Venus's role in humanity's broader expansion throughout the solar system and eventually beyond. The plan envisioned Venus not merely as a self-contained civilization, but as a crucial node in an expanding network of human settlements, contributing its unique expertise and perspective to collective efforts spanning multiple worlds. Specific initiatives included expanded shipbuilding capacity in the floating shipyards to support interplanetary transport, research into long-duration life support technologies applicable to potential interstellar missions, and philosophical frameworks for ethically engaging with potentially habitable worlds beyond the solar system. This expansive vision reflected both confidence born of 150 years of successful adaptation and humility derived from the same experiences. The colony had achieved what once seemed impossible, a thriving human civilization in the clouds of Venus, but had done so through measured steps, careful planning, and willingness to learn from setbacks and challenges. This same approach would guide the next 50 years of development, balancing ambition with pragmatism as Venus continued its remarkable journey. As year 150 concluded, the Venus colony stood as perhaps the most extraordinary achievement in human history, a flourishing civilization in an environment that, by all traditional measures, should have been utterly hostile to human life. From the deployment of Cloud Haven 1 to the integrated cloud metropolis, from the first tentative steps toward resource self-sufficiency to a thriving industrial economy, from a small outpost of Earth to a sovereign society with its own identity and aspirations, the journey had transformed both Venus and humanity's understanding of its own potential. The golden clouds that had once seemed an impenetrable barrier had become home to generations who knew no other world. The environment that had threatened the earliest explorers with its acid rains and searing heat had become a familiar neighborhood navigated with confidence born of deep understanding. The planet that had been viewed primarily as a scientific curiosity had become a branch of human civilization with its own contributions to the species' collective journey. As Venusians looked toward their next century among the clouds, they carried forward the legacy of adaptive ingenuity, ethical consideration, and persistent optimism that had enabled their world to exist at all. Whatever challenges and opportunities the future might bring, the floating cities of Venus had demonstrated one truth beyond question. With sufficient creativity, courage, and care, humanity could make a home among even the most unlikely stars.